Everything you've ever touched feels solid, but it's a beautiful lie. Matter is mostly empty space, held together by forces you can't see. Peel reality back past atoms, past electrons and photons, and the rules start to break. When you reach quarks and the quantum fields beneath them, are you finding the universe's final building blocks, or the edge of what can ever be known? In the next heartbeat, your world will shrink by powers of 10, until even distance starts to lose its meaning. We are going to chase the smallest actors in nature, where reality answers in statistics and silence, not with a microscope, but with collisions, because at these scales to look is to strike. Each step downward forces a trade, more resolution, more energy, more disturbance, and fewer comforts from common sense. Here, the universe does not present tiny marbles hidden inside matter. It offers behaviours, charges that repel without touching, bonds that form without gears, and stability that depends on rules you cannot bargain with. We will follow the evidence the way physics learned to follow it, through spectra that fingerprint atoms across starlight, and through scattering patterns that betray what cannot be photographed. In these measurements, nature leaves clues like footsteps in snow, crisp at first, then stranger as the ground itself changes. Atoms will appear not as indivisible points, but as architecture, mostly space, yet stubbornly structured by discrete steps of energy. The familiar table of elements will become a map of allowed possibilities, drawn by constraints that never announce themselves to the eye. Then comes the electron, restless, precise in its effects, elusive in its whereabouts, forcing us to speak in amplitudes instead of trajectories. Its location becomes a question asked to an experiment, answered only with a click, and never without consequence. Light will not merely illuminate this descent, it will become part of the story's machinery. A photon can behave like a wave and arrive like a particle, and the boundary between those descriptions will prove to be negotiable only at a price. Deeper still lies the nucleus, a locked room where enormous energies hide in a space smaller than imagination. There, neutrons change the fate of elements, and the strong force keeps order with rules that feel almost personal, short-tempered, absolute, and unforgiving. And when we finally reach quarks, the language shifts again, because what we call a particle may be only the name of a pattern in a field. The standard model will appear as a triumph of symmetry and prediction, and also as a reminder of what it does not yet explain. Through it all, we will keep one question in view. When matter dissolves into interactions, what remains that can honestly be called fundamental? The closer we get to the bottom, the more the universe resembles a set of relationships, written in probability, enforced by symmetry, and tested by machines built to listen for the faintest, briefest signs. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. This is a guided fall through atoms, electrons, photons, neutrons, and quarks, then toward the edge where even space-time becomes uncertain. What we find will not be a final object, but a deeper way of reading what the universe permits. A hand meets a door and the door refuses to yield, as if the world is made of uninterrupted substance. The skin compresses, the knuckles pale, and the surface answers with a blunt, immediate resistance. It feels like certainty, like continuous material, like a simple fact you never needed to question. But the first crack in the story is this. Almost everything you call solid is mostly empty space. Not metaphorically empty, and not empty in the everyday sense of nothing there. Empty in the geometric sense. Vast separations between the places where mass and charge tend to reside. If you could shrink without limit, the door would not become denser in a smooth, uniform way. It would become stranger, more structured, and more conditional, an architecture held together by rules rather than by bulk. The closer you look, the more solid begins to sound like a behaviour, not a substance. At human scale, matter looks smooth and complete, like a painted plane with no seams. At smaller scales, it becomes a lattice of atoms spaced far apart compared with their own sizes. The wood grain becomes a terrain, then a grid, then a statistical crowd of repeating units. An atom is not a tiny billiard ball rolling through space. It is a dense nucleus surrounded by electrons that do not orbit like planets, because quantum mechanics forbids that simple picture. Instead, Electrons occupy standing wave patterns, regions where they are likely to be found, and regions where they almost never appear. Between nucleus and electrons is a gulf, and the gulf is not filled with hidden material. The stability comes from forces and quantum rules, including the fact that electrons can only take certain energy states. In plain terms, the atom is mostly open volume, yet it behaves like a reliable building block. So why does the door feel solid, even though its atoms are mostly space? Because electromagnetic forces push back when electron clouds overlap, and because quantum states resist being compressed. Your hand never reaches the nuclei in the wood, because long before that, electric repulsion and quantum constraints rise like an invisible wall. The illusion is not that matter is unreal, or that the door is imaginary. The illusion is that solidity is made of continuous stuff, rather than arrangement and constraint. What you experience as hardness is a collective response, a coordinated refusal encoded in the interactions of countless charged particles. To see the scale, start with a meter, then a millimeter, then a micrometer, and keep dividing. Let the camera glide downward as the door's surface becomes a landscape of ridges and valleys. Keep going until a single human hair becomes a canyon rim, thick as a bridge deck. Keep going until cells become crowded cities of molecules, with membranes like walls and proteins like machines. In this descent, the familiar world dissolves into chemistry, and chemistry dissolves into physics. The image shifts from surfaces you can touch to structures you can only infer. Keep going until molecules resolve into atoms, and atoms into their parts, and the word object starts to lose its meaning. At roughly 1/10 of a nanometer, the atom sets the scale of chemistry. That scale decides what bonds form, what materials are rigid, and what life can build from carbon, oxygen, and hydrogen. Then the descent continues, and the proportions become almost absurd. The nucleus is about 100,000 times smaller than the atom itself. If an atom were the size of a stadium, the nucleus would be a small bead near the center, while the electrons would be patterns spread through the stands. That ratio matters, because it means most of the atom is empty in volume. It also means most of mass is packed into a tiny core, concentrated so intensely that ordinary intuition fails. The door's weight, and your own weight, come mostly from nuclei you never directly touch. Inside the nucleus are protons and neutrons, bound in a tight quantum assembly. Around it are electrons, and around them are probabilities, because quantum theory describes outcomes rather than definite paths. The atom is not a miniature solar system, but a layered set of constraints that only look classical from far away. A proton carries positive electric charge, and that charge shapes the atom's chemical identity. An electron carries negative charge, equal in size and opposite in sign, and the balance between them makes atoms electrically neutral. The attraction between opposite charges holds electrons near the nucleus, but not in the way a planet is held by gravity. A neutron carries no net electric charge, but it is not neutral in its internal structure. It is a composite object with moving parts, and its internal charges and currents matter for how it interacts. Neutrons help stabilize nuclei, because protons repel one another electrically, and the nucleus needs an additional binding mechanism. Photons are different, and their difference is a clue. They are quanta of light, and also the carriers of the electromagnetic force, meaning they mediate how charged particles influence each other. In visual terms, photons are the messengers that let charges feel one another across space. When atoms absorb or emit photons, they do it in discrete steps, because electron energy levels are quantized. Those steps create spectra, and spectra become fingerprints of matter, with lines at specific colors and frequencies. A prism or a diffraction grating turns invisible structure into visible bars of light. This is the first method. We learn the invisible by reading the light it leaves behind. Astronomers use spectral lines to identify elements in the sun before they could ever sample it. In laboratories, the same lines reveal electron transitions, and they quietly confirm that energy comes in packets. The second method is scattering, and it is as physical as throwing stones into darkness. We throw particles at targets and infer structure from the angles and energies that return. A tight, heavy center scatters projectiles differently than a diffuse cloud, and the pattern becomes a map. This approach has a history, and it changed the story of the atom. Rutherford's gold foil experiment showed that most alpha particles pass through, while a few bounce sharply, implying a compact nucleus. The atom, once imagined as a uniform pudding of charge, became a mostly empty stage with a dense centre. The third method is acceleration, and it is a modern extension of the same logic. We build machines that push particles near light speed, then collide them to reveal new fragments and patterns. Energy becomes a probe, because shorter wavelengths and higher momenta can resolve smaller distances. CERN matters because it is a controlled storm, engineered with magnets, vacuum pipes, and detectors layered like digital armour. It concentrates energy into tiny volumes, recreating conditions closer to the early universe. On screens, collision events bloom as tracks and sprays, like fireworks drawn in mathematics. That connection is not poetic, and it is not just a slogan for a museum wall. It is literal physics, because energy can become matter, and matter can become energy. Einstein's relation is not a philosophical statement, but a bookkeeping rule that experiments confirm again and again. In the beginning, the universe was hot enough that atoms could not exist. It was a particle soup of quarks, gluons, electrons, photons, and neutrinos, all colliding too violently for stable structures. In that era, solid was not even a meaningful concept, because there were no atoms to assemble into solids. As the universe expanded, it cooled, and cooling changed what could bind and what could persist. Quarks became confined into protons and neutrons, and later those nucleons formed the first light nuclei. Much later still, electrons could settle into atomic states, and the universe became transparent to light. The content of matter and energy set the cosmic outcome, and small differences mattered. Tiny asymmetries in particles and forces determined whether galaxies could grow and whether stars could ignite. It is striking to ask how close the cosmos might be to a version where chemistry never gets started. Gravity gathered gas into stars, but gravity alone could not make chemistry. Chemistry needs electrons, stable nuclei, and the electromagnetic force acting over the right ranges. Without quantized electron shells, there are no reliable bonds, no complex molecules, and no long-lived information structures. Inside stars, nuclear reactions fuse light nuclei into heavier ones, releasing energy that makes starlight. Those reactions depend on the strong force and the quantum tunneling that enables fusion at temperatures lower than classical physics would require. Even in a star, quantum probability quietly shapes the fate of matter. When stars die, they seed space with elements, scattering them through stellar winds and explosive ends. Those elements become planets, oceans, and the carbon-based structures that can store information. The calcium in bone and the iron in blood are not just chemicals, but records of ancient stellar interiors. So the smallest scales are not a side story. They are the rules that decide what the universe can become. The door under your hand is connected by a chain of physical necessity to the first seconds after the Big Bang. When you press on the surface, you are testing laws written into the earliest conditions. To map those rules, modern physics uses the Standard Model, a framework built from decades of experiments and careful theory. It is our best inventory of known particles and three fundamental forces. It names the actors, specifies their charges, and predicts how they interact in quantized fields. It describes electromagnetism, the weak force, and the strong force, each with its own carrier particles and signatures. It does not include gravity in a quantum way, and that absence is not a footnote. Gravity shapes the cosmos at large scales, yet it resists the same quantized description that works for the other forces. The Standard Model is powerful because it predicts results with extreme precision, often to many decimal places. It is incomplete because it leaves key questions unanswered, even while matching data with astonishing accuracy. That combination, success and incompleteness, is part of the mystery that keeps the field alive. It does not explain dark matter, which outweighs ordinary matter in the cosmos and reveals itself through gravity. It does not explain dark energy, which drives cosmic acceleration and stretches space itself. These are not minor corrections because they dominate the universe's energy budget. It does not explain why there is more matter than antimatter when the equation suggests symmetry. It does not explain why the constants have the values we measure rather than slightly different values that might erase stable atoms. Each gap is a question posed by reality, and the Standard Model answers only part of it. Still, it is the best map we have of the small, drawn from collisions, decays, and the patient accumulation of evidence. It tells us what is elementary and what is built from deeper parts. It also tells us where our confidence is high and where the fog begins. In particle physics, an elementary particle is not defined by size, because size becomes slippery. It is defined by having no known internal structure in experiments so far, within the resolution we can achieve. Elementary means no subparts detected, not simple in the everyday sense. Electrons appear elementary, and their behavior is described by a quantum field that fills space. Photons appear elementary, and they emerge as excitations of the electromagnetic field. Quarks appear elementary, but they never appear alone, and that fact is not a technicality but a defining feature of the strong interaction. Protons and neutrons are not elementary, even though they feel fundamental in ordinary life. They are made of quarks bound by gluons, held by the strong force in a regime so intense that calculation becomes difficult. A proton is a seething system of fields and virtual particles, not three beads glued together. Quarks come in types called flavors, and the names are historical artifacts of discovery. They also carry a charge called color, which has nothing to do with visible color. Color charge is a way of labeling how quarks participate in the strong force, and it comes in combinations that must balance. Color charge is the bookkeeping of the strong force, but it is more than accounting. It explains why quarks are confined inside composite particles, and why the force does not fade with distance the way electromagnetism does. In this domain, pulling harder does not separate components, it stores energy in the field. Confinement is one of the strangest facts in nature, and it reshapes what particle means. Pulling quarks apart does not free them, it creates new quark pairs, turning energy into matter in a cascade. The attempt to isolate a quark becomes a factory for more hadrons, as if the vacuum refuses to reveal a single coloured charge. The deeper we look, the less reality behaves like objects in space. It behaves like fields, interactions and quantized outcomes where particles are excitations and measurements are events. The door's solidity begins to look like a macroscopic summary of microscopic field behavior. This is where the narrative tension begins. Because every time physics improved its microscope, the world became less intuitive. Atoms were once proposed as indivisible units, a philosophical guess that later became a scientific hypothesis. Then, experiments showed atoms have parts, and those parts obey quantum rules that defy common sense. Classical physics expected certainty, with trajectories that could be predicted if you knew the starting conditions. Quantum physics replaces certainty with probability, and replaces trajectories with wave functions that encode possible outcomes. The equations do not tell you what will happen, but what can happen, and with what likelihood. Wave-particle duality is not a metaphor designed to sound mystical. Electrons and photons can act like particles in one experiment and like waves in another, depending on what you measure. The same entity leaves a localized dot on a detector, yet builds an interference pattern over time. The double-slit experiment is the warning sign, and it remains unsettling even after you learn the math. It shows interference patterns from single particles, as if each particle explores multiple paths. The pattern is not painted by crowds alone, because it appears one detection at a time, accumulating into a wave-like signature. Then measurement enters, and the pattern changes, as if the universe updates its answer when you ask a different question. The act of observing is not passive, because it changes which quantum possibilities survive. What counts as which path information becomes a physical interaction, and the system responds. Uncertainty is not just a technological limit that better instruments could overcome. It is built into the structure of quantum theory, linking what can be known about position and momentum. The more tightly you pin down one, the more the other spreads, not by choice but by principle. At small scales, energy comes in quanta, and that quantization stabilizes matter. Forces are exchanged by particles, and the vacuum is not empty in the classical sense. Even when you remove atoms, fields remain, and those fields can fluctuate within the limits set by quantum rules. Even empty space has fields, fluctuations, and constraints, and those constraints have measurable consequences. The door feels solid because empty space is governed by strict rules, including the Pauli exclusion principle that prevents electrons from piling into identical states. In plain language, matter has personal space enforced by quantum mechanics. So what are we really touching when we press a hand to wood or steel? We are touching electromagnetic repulsion, quantum exclusion, and the collective behavior of countless electrons. The sensation of contact is a negotiation between fields, mediated by photons and stabilized by the structure of atoms. This chapter is a doorway, not a destination, and it is meant to reframe the obvious. It frames the problem, and it sets the stakes from the atom to the cosmos. If solidity is an emergent effect, what else in daily life might be an emergent surface over deeper rules? We will move from the familiar to the fundamental, but we will do it with evidence rather than intuition. We will ask what an atom is, then what a nucleus is, then what a proton is. Each question is a step downward in scale, and a step upward in conceptual strangeness. We will meet electrons as both particle and wave, and we will watch their behaviour imprint itself on detectors. We will meet photons as light and as force carrier, and we will treat light as a physical participant. We will meet neutrons as nuclear glue and as a window into the strong interaction. We will meet quarks as the hidden ingredients of ordinary matter, and we will confront the fact that they cannot be isolated. And we will keep asking a single question, because it is the question that survives every new instrument. What is everything made of when you keep dividing, and what laws decide the answer? The method will be evidence, not intuition, and the evidence has recognizable signatures. Spectra will tell us about energy levels, scattering will reveal size and shape, accelerators will expose new states. Each technique is a translation device, turning invisible dynamics into patterns we can record. Each tool has limits, and those limits matter, because they shape what questions can be asked cleanly. At extreme energies, new particles appear, but interpretation depends on theory and statistics. A detector does not show a particle directly. It shows a track, a timing signal, and a spray of energy deposits. At extreme smallness, measurement itself becomes part of the system, and the boundary between observer and observed blurs. The closer we look, the more we disturb what we are trying to see. That is not a defeat, because it reveals that information has a cost, and that nature enforces it. That is not a defeat. It is a clue about how reality is stitched together and why the world is stable at all. The illusion of solid is the first clue, because it is an everyday experience that points directly at quantum law. It tells us that the ordinary world is a macroscopic compromise, not a fundamental layer. Now we step through the doorway. If the universe is built from atoms, what is an atom really, and how did we learn it was not indivisible? Chapter 1 left us with a paradox that refuses to go away, because everything feels solid while solidity is mostly empty space and strict rules. When you press a fingertip against a table, nothing obvious gives way, yet the contact is really an encounter between fields. The surface looks continuous in daylight, but at atomic scale it is a landscape of separations, constraints, and probabilities. The question is not whether matter is real, but how reality can be built from so much apparent emptiness. For most of human history, the atom was an idea before it was a thing, and ideas can travel farther than instruments. Greek thinkers used atomos to mean uncuttable, a last unit beneath division, and the word carried a promise of finality. In that ancient picture, you could keep slicing matter in thought until you reached a boundary that could not be crossed. That word carried no measurements, no error bars, and no experimental handles. Philosophy could name the boundary, yet it could not prove it existed, because proof requires a way to make nature answer. Even the concept of element was different then, tied to qualities and categories rather than counts and ratios. Centuries later, chemistry began to narrow the mystery into numbers, and numbers have a way of forcing precision. Elements combined in fixed ratios, and reactions behave like counting rather than smearing, as if matter arrived in discrete packets. When copper and oxygen formed a compound, the masses did not drift continuously, but locked into repeatable proportions. That regularity became a quiet pressure on theory, because it suggested that nature was doing arithmetic. Lavoisier's conservation of mass made the bookkeeping strict, and Proust's law of definite proportions made it stubbornly consistent. If matter were infinitely divisible in practice, why would it assemble into such clean, repeatable recipes? Dalton turned that regularity into a model of discrete units, and his move was both simple and radical. Atoms explained why water always formed in the same proportions everywhere, because the ratio was built into the count of units. In Dalton's view, compounds were not blends but assemblies, and chemistry became architecture rather than alchemy. Still, atoms remained a convenient fiction to many scientists because convenience is not the same as existence. If you could not see them, some argued, you should not build reality from them, especially when other models could mimic the same chemical laws. The debate was not merely stubbornness, because 19th century science had learned to distrust invisible entities that explained too easily. The turning point came from motion that looked like noise, a kind of restless choreography inside the ordinary. In a microscope, pollen grains jittered in water, never settling into stillness, even when the fluid seemed calm. The motion was irregular, changing direction without warning, as if the particle were being tapped by an invisible crowd. At first, it was tempting to blame life, convection, or hidden currents, because the eye looks for familiar causes. But Brownian motion was not life or secret flows, and it did not disappear when the particles were dead or the water was still. It was the statistical push of countless invisible impacts from molecules in thermal motion, each collision tiny, yet together unmistakable. Here the word thermal matters, because temperature is not a substance but a measure of microscopic energy. Even in a room that feels quiet, molecules are moving at hundreds of meters per second, colliding, rebounding, and exchanging momentum. The pollen grain is massive by comparison, so it responds slowly, but it cannot avoid the cumulative imbalance of random hits. Einstein treated the jitter as a measurable signature of atoms, and he did it with equations that turned randomness into prediction. He connected the average displacement of a particle to time, temperature, and fluid viscosity, and he showed how diffusion could reveal molecular reality. What looked like aimless wandering became a statistical law, and that law depended on the existence of discrete molecules. Perrin tested it, counted it, and helped turn atomic theory into evidence, using careful measurements and repeated trials. By comparing observed motion with Einstein's formulas, he could estimate Avogadro's number, the scale of how many molecules fit into a macroscopic amount of matter. The result did not merely support atoms, it pinned them to a numerical address in the world. That proof mattered because it changed the rules of argument, and science is often about rules of argument. Atoms moved from plausible explanation to unavoidable component of physical law, because multiple independent measurements converged on the same conclusion. When different techniques agree, the invisible begins to feel less like speculation and more like structure. Another line of evidence arrived through light, which is both messenger and interrogator. When heated gases glowed, they did not produce continuous colour but precise lines, bright and narrow against darkness. In a lab, a discharge tube can look like a simple neon shimmer, yet a spectroscope reveals a hidden code. Spectroscopy revealed that matter had internal structure, and it did so with a clarity that was hard to ignore. Each element stamped light with a pattern, like a barcode written in frequency, and the pattern repeated across instruments and continents. The same gas produced the same lines, as if atoms carried an internal set of permitted notes. Those lines were not artistic quirks of flame, and they were not artifacts of glass or prism. They were the first public hints that energy inside atoms came in discrete steps, because only discrete steps can yield discrete photon frequencies. A continuous range of internal energies would smear light into a continuum, but nature insisted on sharpness. By the late 19th century, the atom was real enough to be interrogated, and interrogation requires a new kind of question. The next question was structure, because spectra implied hidden layers, and chemistry hinted at internal organization. If atoms were truly indivisible, why would their light carry such detailed signatures? Early models tried to keep the atom classical, because classical physics had explained so much already. Thomson proposed a diffuse positive charge with electrons embedded, a neutral pudding of charge, and it offered a way to place the newly discovered electron inside matter. The model was visually comforting, like raisins suspended in dough, and it preserved overall neutrality. But comfort is not a substitute for accuracy, and experiments began to throw projectiles into the dark. Rutherford fired alpha particles at thin gold foil and watched deflections, using a setup that was almost austere in its simplicity. A radioactive source, a sheet of metal, and a screen that flashed when struck. Yet the results rewrote the atom. Most particles passed through as if the atom were open volume, and that alone was surprising. A few deflected at large angles, and a tiny number bounced back sharply, as if they struck a compact, massive centre. Rutherford compared it to firing a shell at tissue paper and having it rebound, an image that captures the shock of the data. The conclusion was unavoidable and unsettling, because it forced a radical change in scale. Almost all mass and positive charge sat in a tiny nucleus, with electrons occupying the surrounding space, and the atom became mostly emptiness. The The centre was not a diffuse pudding, but a concentrated core with enormous density. This was the first clear map of the atom's architecture, and it arrived not by seeing the nucleus directly but by inferring it from trajectories. It was not a solid sphere, but a layered system with extreme scale separation, where the centre and the outskirts barely shared the same notion of size. The atom's radius is measured in angstroms, while the nucleus is measured in femtometers. If an atom were the size of a stadium, the nucleus would be a bead near midfield, and the electrons would be a kind of structured haze. The rest would be mostly empty, yet not meaningless, because emptiness can still be governed. In that vast interior, forces act, constraints apply, and probabilities shape what can happen. That emptiness is not a void of physics, and it is not an absence of law. It is a region governed by electromagnetic fields and quantum constraints that decide where electrons can be and where they cannot. The space is empty of matter in the everyday sense, yet full of influence, like a stage filled with invisible choreography. The next model tried to explain why electrons did not fall into the nucleus, because classical electrodynamics made collapse seem inevitable. An accelerating charge should radiate energy, and an orbiting electron is accelerating, so it should spiral inward and crash. Bohr proposed quantized orbits, allowing only certain energies and radii, and he did it by imposing a rule that classical physics did not naturally provide. Bohr's model predicted hydrogen's spectral lines with striking success, which gave the quantization idea a sudden legitimacy. It also exposed a deeper rule, that energy levels were not continuous, and that electrons could jump between them without occupying the space in between. The jumps looked strange, but the lines on the spectroscope were stranger if you refused them. Yet the planetary picture was still a compromise with intuition, a visual metaphor that worked until it did not. It worked for simple atoms, then broke when complexity and precision increased, because multi-electron interactions and fine details demanded more than circular tracks. Even hydrogen revealed subtleties, like fine structure, that hinted at deeper mechanics. Quantum mechanics replaced orbits with states, and the replacement was not cosmetic. Electrons were not tiny planets tracing paths, but quantum objects described by probability distributions, and the language of trajectories gave way to the language of amplitudes. In this framework, the atom is not a miniature solar system, but a bound quantum system with discrete solutions. An electron in an atom is represented by a wave function, a mathematical object that evolves smoothly until measurement intervenes. The wave function does not give a track. It gives likelihoods for measurement outcomes, which is a different kind of description. It tells you where the electron is likely to be found, and how its momentum is distributed, without claiming it had a definite path all along. Orbitals are not miniature rings in space, and they are not literal clouds you could scoop. They are standing wave patterns shaped by energy, angular momentum, and the atom's electric field, and they can have nodes where the probability drops to zero. The familiar shapes, spheres, dumbbells, and more intricate forms are visual translations of mathematical symmetries. This is where language starts to strain, because our everyday nouns assume definite locations. The electron is localized when detected, but it is spread out in the mathematics between detections, and that spread is not mere ignorance. It is a real feature of the theory, confirmed by interference and by the stability of atomic structure. The atom becomes a system of allowed possibilities, and its stability comes from quantized energy levels and the rules that govern transitions. Those rules include selection rules, which constrain which jumps are likely, and which are forbidden, based on angular momentum and symmetry. Even when an electron can transition, it does so with characteristic probabilities that shape line intensities. Those rules are not optional details because the world depends on them. Without quantization, electrons could radiate energy continuously and spiral inward, and chemistry would collapse, leaving no stable atoms to build molecules. The periodic table would lose its pattern, and the rich diversity of materials would flatten into something unrecognizable. So the atom is the first layer of invisible architecture, and it sits at a critical boundary between scales. It is the bridge between everyday materials and the deeper laws that build them, because it is small enough for quantum effects to dominate and large enough to assemble into bulk matter. When you hold a metal key or watch water boil, you're watching atomic rules expressed at scale. To connect that architecture to the cosmos, we have to rewind time. The early universe was too hot for atoms because electrons could not stay bound, and energetic photons would immediately tear them loose. In that primordial furnace, matter existed as a plasma, a soup of nuclei and electrons coupled tightly to radiation. In the first minutes after the Big Bang, nuclear synthesis forged light nuclei, and it did so under rapidly changing conditions. The outcome was mostly hydrogen, a large fraction of helium, and traces of lithium, because the universe expanded and cooled before heavier nuclei could form efficiently. The timing mattered, because the window for fusion closed as density dropped. This distribution was not a guess, it was a prediction, and predictions can be compared with observation. It depended on expansion rate, particle densities, and the competition between reactions and cooling, including the balance between protons and neutrons as the universe aged by seconds. A small change in those early conditions would have left a different cosmic inventory. For hundreds of thousands of years, the universe remained an ionized plasma, bright yet opaque in a very specific way. Nuclei and electrons existed, but light scattered constantly and could not travel far because free electrons are efficient at scattering photons. Space was filled with radiation that could not stream freely, trapped in a continual exchange with charged particles. Then temperature dropped enough for electrons to bind to nuclei, and binding is a triumph of cooling. This epoch is called recombination, and it produced the first stable neutral atoms, mostly hydrogen and helium, across a universe that suddenly changed its optical character. The name is slightly misleading because it was the first combination on cosmic scale, not a reunion. Recombination changed the universe's behavior in a single step, and the step was dramatic in consequence. Once atoms formed, photons stopped scattering so often, and space became transparent, allowing radiation to travel long distances without constant interruption. The universe did not become dark, but it became readable, because light could finally carry information across expanding space. The light released then still fills the universe now, stretched by cosmic expansion into microwaves. We call it the cosmic microwave background, a cooled relic of the moment atoms first held electrons, and it is astonishingly uniform. When instruments map it, they reveal a faint afterglow that seems to come from every direction at once. The microwave background is not just a picture of early time, and it is not merely a pretty texture on a sky map. It is an imprint of matter and radiation decoupling, tied directly to atomic binding, because neutral atoms scatter light far less than free electrons do. In that sense, the first stable atoms acted like a switch that turned the universe transparent. Its tiny temperature variations record density ripples, and those ripples are the seeds of structure. Those ripples later grew into galaxies, meaning atomic physics helped set the stage for cosmic structure, because the timing of recombination affects how matter clumps. When we study those patterns, we are reading a fossil record written in photons, so atoms are not merely chemical units on Earth, and they are not parochial features of one planet's laboratory. They are milestones in cosmic history, marking when the universe could finally carry light across distance, and when matter could begin to separate into the large-scale forms we see. In a real sense, atoms are part of the universe learning to become transparent to itself. Once the universe had neutral atoms, gravity could gather gas into stars, because neutral gas can cool and collapse more effectively. Inside stars, nuclear fusion built heavier nuclei, but atoms remained the interface to light, shaping how energy escapes. A star's spectrum is not a decorative surface, but a diagnostic report of its outer layers. Starlight is not a generic glow, even when it looks white to our eyes. It is filtered and shaped by atomic transitions, because electrons absorb and emit photons at specific energies, and those energies correspond to particular wavelengths. The colours we see are a compressed summary of a much richer distribution. A photon carries energy proportional to its frequency, a relation captured by Planck's constant. When its energy matches a gap between electron levels, it can be absorbed, lifting the electron upward into an excited state. The atom does not absorb some of the photon, because the exchange is quantized, and the match must be exact within the line's natural width. When the electron drops back down, a photon is emitted, and the emitted photon's frequency matches the energy difference. That difference produces a discrete spectral line, and the line's position is a precise marker of atomic structure. The same transitions occur in a laboratory lamp and in a distant nebula, because the underlying quantum rules are the same. In dense matter, collisions broaden lines and shift them, because atoms are jostled and energy levels are perturbed by nearby particles. In thin gases, lines stay sharp, and the pattern becomes a clean fingerprint of the element, with narrow features that can be measured to high precision. Even the broadening itself is informative because it encodes temperature, density, and pressure. Absorption lines appear when a cooler gas sits in front of a hot source, such as a star's photosphere behind a cooler atmosphere. The gas removes specific frequencies, leaving dark gaps in an otherwise bright spectrum, and those gaps align with the atom's permitted transitions. What looks like missing light is actually evidence of selective interaction. Emission lines appear when excited atoms radiate in isolation, such as in a glowing nebula energized by nearby ultraviolet starlight. The same element can write its identity in either darkness or brightness, depending on conditions, and the pattern remains recognizable. In both cases, the atom acts like a filter with a highly structured passband. This is how astronomy reads chemistry across impossible distances, turning light into a remote laboratory. We cannot scoop the sun, yet we can identify sodium, hydrogen, and helium by their lines, and we can estimate temperatures from relative intensities. A spectrum is not just a list of elements, but a thermodynamic and kinematic snapshot. Helium was discovered in the sun's spectrum before it was found on Earth, and the historical irony is instructive. That fact is a reminder that atoms announce themselves through light, and that nature can reveal new substances without direct sampling. A thin, dark line in sunlight became a claim about a new element, and later chemistry confirmed it. Spectra also reveal motion, because motion changes the received frequency. Doppler shifts slide the lines, letting astronomers measure speeds of stars, galaxies, and expanding gas clouds, even when the objects are too distant to resolve. A tiny shift in wavelength becomes a statement about kilometers per second. Spectra reveal magnetic fields through splitting, and the effect is subtle but powerful. The Zeeman effect shows that atomic energy levels respond to fields, turning light into a probe of invisible forces, and the amount of splitting can be used to estimate field strength. In this way, atomic structure becomes a sensor for conditions that cannot be touched. So a simple atom becomes a universal instrument, and its reach is astonishing. It links laboratory physics to cosmic history, because the same transitions occur in distant nebulae, in stellar atmospheres, and in the controlled glow of a discharge tube. The universe is not a separate domain with separate rules, but a larger stage for the same quantized interactions. Yet the atom's structure forces another paradox, one that returns us to the table beneath your hand. If it is mostly empty space, why does matter resist compression and feel hard to the touch, instead of yielding like mist? The answer is not that atoms are little billiard balls packed tightly, because they are not. The first answer is electromagnetic repulsion, and it is immediate at close range. When electron clouds approach, like charges repel, and the force rises sharply at small separations, because the electric field grows stronger as distance shrinks. In solids, the arrangement of atoms is partly a balance between attraction and repulsion, and that balance sets typical interatomic spacing. But repulsion alone is not the full story, because classical repulsion does not explain the full stiffness of matter. Quantum mechanics adds a rule that is not a force, yet it behaves like one in bulk matter, and it is rooted in identity rather than charge. This rule is not about pushing, but about counting allowable states. The Pauli exclusion principle forbids identical fermions from sharing the same quantum state, and electrons are fermions. Electrons cannot all collapse into the lowest energy arrangement, even if attraction would prefer it, because the quantum numbers must differ. This principle is why electron shells fill in a structured order, and why the periodic table has repeating patterns. As you try to squeeze matter, you force electrons into higher momentum states, because the available low momentum states become occupied. That increase in energy produces pressure, even at zero temperature, and the pressure resists further compression. In plain terms, the electrons run out of room in state space, and the system pays an energy cost. This is degeneracy pressure, and it appears in ordinary solids and in extreme stars, though the scale changes dramatically. It is a quantum refusal built into the identity of electrons, and it does not require heat to operate. The same principle that stiffens a metal also helps support white dwarf stars against gravitational collapse. So the sensation of solidity is a macroscopic effect, and it is an emergent one. It emerges from electromagnetic interaction and quantum exclusion, not from continuous substance, and it is strongest when many atoms cooperate in a lattice. What feels like a single rigid surface is really a collective response of countless electrons constrained by shared rules. The nucleus contributes almost all the mass, but almost none of the volume, which is another way the atom defies intuition. Its size is about 100,000 times smaller than the atom's radius, a ratio that is hard to hold in the mind. If you could shrink yourself to the scale where an atom is a room, the nucleus would be a speck of dust. That ratio is not a trivia fact, it is the geometry of everyday life, because it tells us where contact happens. It means contact happens in electron clouds, far from nuclear surfaces, and chemistry lives in that outer region. When atoms bond, they do not merge nuclei, they share and rearrange electrons in the spacious outskirts. Inside the nucleus, protons and neutrons are bound by the strong interaction, and the binding is intense. Electric repulsion between protons would tear nuclei apart without that binding, because like charges repel strongly at short distances. The strong force acts over tiny distances, yet it dominates nuclear stability, and it is why nuclei can exist at all. Neutrons matter because they add binding without adding electric repulsion, and their presence changes the balance of stability. They change nuclear stability and enable a wide table of elements, because different proton counts require different neutron counts to remain bound. The fact that isotopes exist, stable and unstable, is a reflection of that internal competition. But even in this chapter, the nucleus is a signpost rather than a destination, and we can feel the narrative pulling downward. The nucleus is not elementary, and later chapters will open it further, because protons and neutrons have their own internal structure. For now, we stay with the atom as the first stable unit that organizes ordinary matter. For now, the atom is our focus because it is the first stable unit of structure, and it is where quantum rules first become unavoidable in ordinary matter. Quantum mechanics enters gently, but it changes the meaning of explanation, because it replaces certainty with constraint. Instead of predicting exact paths, it predicts distributions of outcomes, and it does so with remarkable consistency. Measurement is not a window that leaves the system untouched, and this is not a mystical claim. To measure position or energy, you must interact, and interaction changes what can be known, because the act of probing exchanges momentum and energy. In atomic experiments, the probe is often a photon or an electric field, and both can disturb the state they reveal. The uncertainty principle is not a flaw in instruments, and it is not a temporary limitation awaiting better technology. It is a constraint on simultaneous knowledge of complementary quantities like position and momentum, built into the mathematical structure of quantum theory. If you confine a wave function in space, you necessarily spread its momentum distribution. In atoms, uncertainty is not a nuisance. It is a stabilizer, and the stabilizing role is concrete. Confining an electron too tightly increases its momentum uncertainty and raises its energy, which resists collapse into the nucleus. The electron's spread is not just tolerated, it is required for a low-energy bound state. That balance helps prevent collapse, and it sets a characteristic scale for atoms. The atom's size is set by a compromise between attraction to the nucleus and quantum spread, and that compromise can be calculated using fundamental constants. When you see matter occupying space, you're seeing the outcome of that compromise repeated trillions of times. So the atom is not a miniature machine with hidden gears, even though our metaphors keep reaching for machinery. It is a set of allowed states, with transitions that exchange photons in discrete packets, and those packets carry precise amounts of energy. The discreteness is not a human bookkeeping trick, because it is enforced by the structure of the solutions. Those packets are not optional bookkeeping, and their consequences are everywhere. Quantization explains why atoms have specific sizes, why chemistry has patterns, and why light carries information in lines and edges. It also explains why materials have characteristic colors, why some substances conduct electricity, and why others insulate, because electron states determine response. The deeper implication is that reality is partly statistical, and the statistics are not a retreat from knowledge. The wave function encodes what can happen, and measurement selects a definite outcome, which is a different kind of causality than classical trajectories. The theory does not say anything happens, because it assigns precise probabilities that can be tested. This selection is not a human choice. It is a physical event, and it happens whether or not anyone is watching. Detectors, atoms, and fields become entangled, and the system yields one result, leaving a record in a macroscopic device. The click of a detector or the flash on a screen is the end of a quantum story and the start of a classical one. We do not need interpretation debates to feel the tension, and we do not need to settle philosophical camps. We only need the fact that the atom's most basic description is probabilistic, even though its outcomes are sharply constrained. The world is not vague, but the underlying description is not a set of definite paths. Yet the probabilistic description is also predictive, and its success is one of the great surprises of modern science. Quantum theory calculates spectra with extreme accuracy, matching lines measured in labs and in Starlight, down to tiny shifts caused by relativity and spin. When theory predicts a line position, and the instrument finds it, the invisible becomes almost tangible. So the atom becomes a proof of method, and method is part of the story. A theory built on probabilities can still yield precise fingerprints, and those fingerprints can map the universe, from laboratory lamps to distant galaxies. The atom is where abstraction meets measurement, and where measurement keeps agreeing. This is why atoms sit at the centre of the documentary's central question, because they are the first layer where everyday matter meets fundamental law. Atoms are also a boundary between scales, and boundaries are where intuition often fails. Above them are materials, biology, and technology, and below them are particles that do not behave like objects. The chapter's historical arc matters because it shows how knowledge is earned, and how the invisible becomes unavoidable. We did not assume atoms, we cornered them with motion, light, and scattering, each method attacking a different weakness in the skeptic's case. The story is not one miracle experiment, but a convergence. Brownian motion made atoms unavoidable in fluids because it translated unseen impacts into measurable wandering. Spectroscopy made internal energy levels unavoidable in light because it turned atomic structure into a pattern of lines. Scattering made the nucleus unavoidable in matter because it made emptiness and concentration visible through deflection. Each method translated the invisible into a record, and the records could be checked and repeated. Jitter became statistics, spectra became lines, and deflections became geometry, and each record carried numerical structure. The atom did not become real because it was pleasing, but because it left consistent traces in independent domains. That translation is a theme we will return to, because smaller scales rarely offer direct pictures. At smaller scales, you rarely see the thing itself. You see its effects on detectors and fields, and you reconstruct the cause from the pattern. The modern view of matter is built from such reconstructions, disciplined by mathematics and constrained by experiment. Now the atom stands before us as a structured system, familiar yet strange, and the visuals almost write themselves. A nucleus at the centre, and an electron cloud described by orbitals and probabilities, with shapes that reflect symmetry rather than mechanical motion. In diagrams, the nucleus is drawn large for clarity, but in reality it is almost unimaginably small. It is stable, but only because quantum rules restrict what electrons can do, and because those restrictions create discrete shells. It is empty in volume, but full of constraints that shape behaviour, and constraints can be as real as walls. The emptiness is why atoms can be mostly space, yet still resist intrusion, because the rules are not negotiable. It is ancient in origin, because the first atoms formed when the universe cooled enough to bind electrons, and that event still echoes in the microwave background. It is cosmic in reach, because its spectra travel across space, and because those spectra tell us what stars are made of. The same atomic transitions that define a lab experiment also define what the cosmos can show us, and it is familiar in consequence, because it determines chemistry, materials, and the illusion of solidity, down to the stiffness of wood and the shine of metal. The atom is the first layer where the invisible becomes reliable, where unseen rules produce repeatable outcomes. It is the smallest unit that still feels like stuff, even though it is mostly not. But the atom also hides its most puzzling actor in plain sight, and the puzzle is not decorative. The electron is everywhere in matter, yet it refuses the classical picture of a tiny orbiting bead, even when our diagrams tempt us to imagine one. It behaves like a particle when detected, yet it must be described like a wave to explain its allowed states. If electrons are not planets, what are they, and what does it mean to be somewhere in a quantum world? Are they objects, waves, excitations of a field, or something that only becomes definite when measured? And why does the question feel unavoidable? When we speak of an electron cloud, are we describing a thing or a rulebook for outcomes? That question is not philosophical decoration, it is the next descent, because the electron is the agent of chemistry and the guardian of emptiness. To go beneath the atom, we have to understand the electron on its own terms, including why it has mass, charge, and spin, and why it obeys quantum statistics. The atom is an arrangement, but the electron is a character. So we take the next step downward. If the atom is mostly empty and built from probabilities, then the electron is the key to the emptiness. And if the electron is the key, then the next chapter must ask what it means to be a particle at all. When particle no longer means a tiny solid bead, the descent continues, and the familiar keeps dissolving, until the rules themselves begin to look like the substance. The electron is the atom's main actor, and it behaves like nothing else we touch. It carries negative electric charge, sets the rules of chemistry, and still refuses any simple picture of location. We can measure it, trap it, and count it, yet we cannot make it sit still. Even when we isolate a single electron, it keeps a kind of restless ambiguity, present, measurable, and stubbornly unlike a tiny ball. Visually, the story often begins in darkness. A vacuum chamber glows faintly with instrument lights, and a detector waits like a blank page. Somewhere inside, a single electron is released, and the entire experiment becomes a question asked of nature. The question sounds ordinary. Where are you? How fast are you moving? But the answer arrives in a language that resists everyday intuition. Start with the most basic attempt at seeing. Any measurement must interact, and interaction means exchange of energy and momentum. If we try to locate an electron tightly, we need a probe with a short wavelength. Short wavelength means high momentum, because wavelength and momentum are inversely related through de Broglie's relation. That momentum kick changes the electron state, and the act of looking becomes an act of pushing. A microscope is a helpful image, but the quantum version is harsher. To resolve small distances, you need light with very short wavelength, like ultraviolet or X-rays. Those photons carry more momentum than visible light, and when they scatter from an electron, they jolt it. The sharper the attempted snapshot, the more violent the disturbance, an unavoidable trade that is built into the structure of waves. This is not a problem of clumsy instruments or incomplete engineering. It is a structural limit built into the mathematics of quantum theory, and it survives every improvement we make. Position and momentum are linked, and their uncertainties cannot both be driven to zero. Heisenberg's uncertainty principle is often written as a compact inequality, but its meaning is broader than a formula. It says that certain pairs of properties are not jointly sharp in the world, even in principle. Historically, this was not an easy idea to accept. Early quantum pioneers working in the 1920s were trying to explain why atoms were stable and why spectra came in discrete lines. Classical physics predicted that orbiting electrons should radiate energy continuously and spiral into the nucleus. Instead, atoms persisted, and their emitted light arrived in precise frequencies, like notes on a scale. The uncertainty principle did not merely patch a theory, it helped redefine what a physical description could be. The uncertainty principle is not a warning label pasted onto a classical world. It is a rule about what reality can jointly specify, and it shows up wherever wave-like descriptions are unavoidable. A wave packet that is narrow in space must be broad in wavelength, and broad wavelength means uncertain momentum. That is not a limitation of our knowledge alone, because it is a limitation of the state itself. The electron is not hiding a perfectly definite position and momentum behind a curtain, waiting for us to become clever. The electron becomes a mystery because it is both real and ungraspable in the classical sense. Each detection is a definite event, a localized outcome on a screen. A single dot appears, sharp and undeniable, as if a tiny grain struck a surface. Between detections, the theory describes a spread of possibilities, not a hidden trajectory. The spread is not ignorance, and it is not a placeholder for missing variables. It is the correct description that experiments keep confirming with relentless precision. Imagine the visual rhythm of a lab run. A source emits electrons so faintly that minutes can pass between impacts, and the detector records each arrival like a ticking clock. The room is quiet, and then a dot appears, and then another and another. Nothing in the individual events tells you what the final picture will be. Yet the final picture, when enough events accumulate, becomes almost eerily stable. Wave-particle duality is the next fracture in intuition, and it is not optional. If electrons were only particles, they would behave like tiny bullets, each one following a definite path. If they were only waves, they would smear out and never make discrete detector clicks. They do both, and the experiment decides which aspect is revealed. The electron is not switching personalities at random, because the setup itself defines what counts as an outcome. The double-slit logic makes the point with brutal clarity. Send electrons one at a time toward two openings and record each arrival. Each arrival is a dot, and each dot looks like a particle hit. Yet the dots accumulate into an interference pattern as if a wave passed through both slits. Bright bands and dark gaps emerge, not because of collisions between electrons, but because of how quantum amplitudes combine. The pattern is not a crowd effect because it appears even when electrons are separated in time. You can slow the source until the electrons are so sparse that they never meet, at least not in any classical sense. The distribution still builds from single events, each one unpredictable yet collectively precise. Quantum mechanics predicts the pattern from amplitudes, not from paths. Probability interferes with itself, and the interference is measurable in the final statistics. To make that idea concrete, it helps to separate probability from amplitude. In quantum mechanics, the wave function is complex valued, and it is the amplitude that adds and cancels like a wave. The probability is the squared magnitude of that amplitude, and it is what we actually observe as counts. Where amplitudes reinforce, the probability grows, and where amplitudes cancel, the probability drops towards zero. In the dark bands of the interference pattern, the electron is not missing because it chose another route. It is missing because the allowed amplitudes cancel. Now add which path information, and the story changes. If the setup records which slit the electron used, the interference disappears. The electron still arrives as dots, but the distribution becomes the sum of two single slit patterns. The change is not psychological, and it is not about a human observer's awareness. The change is physical, because information requires interaction, and interaction entangles the electron with the measuring device. Visually, the difference is striking. With both slits open and no path detection, the screen fills with alternating bands like ripples frozen into statistics. Add a detector at the slits, and the ripples fade into a blunt classical-looking spread. It feels like the universe has decided to stop being subtle, yet it has not changed its mind. It has changed its constraints. This is the hook that keeps returning. Try to see the electron's path, and you change what the electron can do. The world is not hiding a classical answer behind a curtain, because the classical question is not always physically well defined. The world offers different outcomes depending on what is measured, because measurement defines the question in physical terms. In quantum theory, asking is an action, not a passive request. There is a deeper observation hiding here. The electron's behavior forces us to distinguish between what is real and what is simultaneously specifiable. The electron is real in the sense that it leaves tracks, deposits energy, and can be counted one by one. Yet it is not real in the sense of carrying a complete set of classical properties at all times. The mystery is not that the electron is vague, but that the world allows sharp events to emerge from a description that is fundamentally probabilistic. So what is an electron, if it is not a bead following a line? In quantum mechanics, it is described by a state, encoded in a wave function. The wave function is not a picture of a smeared particle drifting like fog. It is a tool that predicts probabilities for outcomes of future measurements. It tells us what we can expect to see and how strongly different possibilities can interfere. The wave function also evolves in a precise way. In many situations, it follows the Schrödinger equation, which is deterministic in its evolution of amplitudes. That determinism is often surprising because the measurement outcomes are not deterministic. The theory is strict about how probabilities flow, even when it refuses to predict a single event. It is as if the script for the distribution is fixed, while the casting of individual moments is left open. In free space, the electron state can spread, interfere, and diffract like a wave. Release an electron from a tight trap, and its wave function expands outward with time, like an ink drop dispersing in water. That spreading is not caused by random kicks from the environment, because it happens even in near-perfect vacuum. It is a direct consequence of the relationship between localization and momentum uncertainty. The electron's refusal to sit still is built into the geometry of its state. In a bound system, the state can form standing patterns that do not radiate away. This is where the atom becomes stable without classical orbits. Stability comes from allowed solutions, not from tiny planets circling forever. The electron in an atom is not a point tracing a loop. but a stationary pattern of probability that can persist indefinitely. The nucleus provides an electric potential, and the wave function settles into discrete self-consistent forms. Orbitals are those allowed solutions inside an atom's electric field. They are discrete because only certain standing wave patterns fit the boundary conditions, much like only certain harmonics fit on a vibrating string. Each orbital corresponds to a quantized energy, and transitions between them require specific energy differences. Those differences match photon energies, which is why spectra are line-like. When we see a sharp spectral line, we are seeing an energy bookkeeping rule made visible. The visual language of orbitals is both beautiful and misleading. We often draw them as lobes and clouds, coloured to show positive and negative phase. But those shapes are not solid objects. They are probability densities, maps of where detections are more likely if we measure position repeatedly. The nodes, where the probability drops to zero, are not empty space in a classical sense. They are places where the wave function cancels itself, enforcing a pattern through interference. The quantum numbers that label orbitals are not arbitrary labels. They arise from symmetries and conserved quantities, including angular momentum and its projections. The principal quantum number organizes energy levels, while the orbital angular momentum quantum number shapes the spatial form. A third quantum number sets orientation, and spin adds another layer of structure. The atom becomes a tightly constrained system, with allowed states that look like a catalogue of possibilities rather than a continuum. Quantization is not decorative, because it builds the periodic table. Electrons fill available states in an ordered way, and that order repeats with increasing nuclear charge. The repeating structure produces chemical families, valence behaviour, and the logic of bonding. Chemistry is quantum bookkeeping that becomes macroscopic pattern. When elements line up in columns, they are echoing the filling of electron shells. There is also a historical resonance here. Mendeleev's periodic table came before quantum mechanics, and it was built from chemical behaviour alone. The table predicted missing elements, and it hinted that nature had a hidden order. Quantum theory later supplied the mechanism, showing that electron configurations repeat because the allowed states repeat. The periodic table is a bridge between 19th century chemistry and 20th century quantum physics, an early map that later gained a deeper legend. Bonding is an electron story, not a nucleus story. Atoms share, exchange, or rearrange electron states to lower total energy. Covalent bonds emerge from shared wave functions and constructive overlap, producing electron density between nuclei. Ionic bonds emerge from electron transfer and electrostatic attraction, creating charged partners that lock together. Metallic bonds emerge from delocalized electrons forming collective states, where electrons are not tied to one atom but belong to the whole lattice. In a covalent bond, it is tempting to imagine electrons as little marbles held between atoms like glue. The quantum reality is subtler. The bond forms because the combined wave function allows a lower energy distribution of electron density, and because the nuclei feel that redistributed charge. The stability is an energy story, told through interference and symmetry. Even the simplest molecule, hydrogen, is a demonstration that sharing a wave function can be energetically cheaper than keeping electrons separate. The electron's refusal to sit still becomes the reason matter has size. Confining an electron too tightly increases momentum uncertainty and raises kinetic energy. That energy cost competes with attraction to the nucleus, setting a characteristic atomic scale. The atom's radius is a compromise between pull and quantum spread. If the electron could be pinned down classically, atoms would be smaller, denser, and fundamentally different. This compromise can be framed in a more physical way. The Coulomb attraction tries to draw the electron inward, lowering potential energy as distance shrinks. Quantum localization raises kinetic energy, because a narrow wave function requires many momentum components. The stable orbital is where these trends balance, producing a minimum in total energy. The size of atoms is therefore not an engineering detail of the universe, it is a quantum equilibrium. Now add spin, a property with no classical analogue that still behaves with strict rules. Spin is intrinsic angular momentum, and it comes with a magnetic moment. It is measured in discrete outcomes, like up or down along a chosen axis. The axis is chosen by the measurement, not by the electron. Rotate the apparatus, and the same electron can yield different statistics, because the question has changed. The Stern-Gerlach experiment is the iconic visual here. A beam of particles passes through a non-uniform magnetic field, and instead of spreading continuously, it splits into distinct spots. That splitting reveals that spin projections are quantized, arriving as discrete outcomes rather than a smooth range. The result looks like a stamp of digital behavior onto an analog world. It is one of the cleanest demonstrations that quantum properties come in counted steps. Spin is not a small sphere literally spinning in space. The electron is treated as point-like in experiments, yet it has spin as a built-in quantum number. Spin enters atomic structure through fine details, splitting energy levels and shaping spectra. It also determines statistics, and statistics determine the architecture of matter. The electron's spin couples to magnetic fields, and it couples to orbital motion through spin, orbit interaction, adding subtle shifts that spectroscopy can resolve. Electrons are fermions, and fermions obey the Pauli exclusion principle. No two identical electrons can occupy the same quantum state in the same system. In atoms, this means each orbital has limited capacity, set by quantum numbers including spin. Shells fill, then new shells begin, and the periodic table emerges again. The table is not just about charge and mass, it is about identity, and the impossibility of perfect duplication within one state. Pauli exclusion is not a force, yet it creates effective resistance to compression. If you squeeze electrons into a smaller volume, available low-energy states fill up. Additional electrons must occupy higher momentum states, raising energy and creating pressure. This is degeneracy pressure, and it is quantum structure expressed as mechanical stiffness. The pressure is not thermal agitation, because it can exist even at very low temperatures. In solids, the same principle helps explain why matter is hard to compress. Electrons in a lattice occupy bands of allowed states, and the lower states fill first. Trying to compress the solid changes the available states, and it forces electrons into different momentum distributions. The resulting resistance is part electromagnetic repulsion and part exclusion-driven energy cost. What we experience as rigidity is, in part, a quantum accounting constraint. This principle scales from solids to stars, and the link is not metaphorical. In white dwarfs, gravity tries to compress matter to extreme density. Electron degeneracy pressure resists, supporting the star without needing thermal pressure. The same exclusion rule that shapes chemical shells helps keep stellar remnants from collapsing further. A white dwarf is, in a sense, a macroscopic object stabilized by the inability of electrons to share the same state. The visuals here shift from laboratory scale to cosmic scale. A white dwarf hangs in space small compared to a normal star but incredibly dense, with mass comparable to the Sun packed into a volume like Earth's. Its light is pale and steady, and its surface gravity is immense. Inside, electrons form a degenerate gas, and their quantum pressure becomes the star's structural backbone. The quiet glow hides a fierce balance between gravity and quantum rules. When exclusion is overwhelmed, the story shifts again. In neutron stars, electrons and protons can combine under pressure, forming neutrons and neutrinos. Neutron degeneracy pressure then becomes the main support. The electron's rules still matter, because the transition depends on electron energies and weak interactions. The collapse is not only a gravitational event, but also a reorganization of quantum states under extreme conditions. So the electron is not just chemistry's agent. It is one of the reasons planets, rocks, and bodies keep their volume. It helps explain why matter does not collapse into a denser state under ordinary conditions. Structure is not guaranteed by bulk. It is enforced by quantum identity, and by the limited ways identical fermions can occupy reality. Yet the electron also mediates forces, and this returns us to the documentary's central question. What is everything made of, if interactions are as fundamental as objects? Electromagnetism is the force we feel as contact, and the electron is its most familiar charge carrier. But in quantum theory, forces are not continuous pushes across space. They are interactions that can be described as exchanges of quanta. In the quantum view, charged particles interact by exchanging photons. The photon is the quantum of the electromagnetic field, and it carries energy and momentum. In everyday light, photons are real particles we can count, and they travel from source to detector. In forces, the exchanged photons can be virtual, meaning they are internal to the interaction and not directly observed. The bookkeeping is different, even though the measurable consequences are the same. Virtual does not mean imaginary, and it does not mean optional. It means the exchange is constrained by quantum rules, not by the classical relation between energy and momentum for free particles. In calculations, virtual photons appear as internal lines in diagrams, representing permitted intermediate processes. The effect is still measurable, because it changes scattering, binding energies, and atomic structure. The force becomes a conversation in quanta, where the grammar is probability amplitude. This is why the door feels solid without your hand reaching nuclei. Electron clouds repel through electromagnetic interaction, and exclusion prevents identical electrons from sharing states. The pushback is mediated by photons, and the allowed states are set by quantum conditions. Solidity becomes an emergent outcome of fields and rules. What feels like a continuous surface is, at deeper scale, a balance of quantum constraints. Electromagnetism also explains why electrons can be accelerated and radiate. When electrons change energy states in atoms, photons are emitted or absorbed with precise frequencies. When electrons are driven in antennas, coherent radio photons are produced, and the field carries energy outward. When electrons are slowed in matter, Bremsstrahlung photons appear, creating X-rays in tubes and radiation in space. The same interaction spans chemistry, electronics, and radiation, linking the smallest transitions to the largest broadcasts. Technology is a direct consequence of electron quantum behavior. Semiconductors rely on band structure, which is a collective set of allowed electron states in a crystal. Conductors have partially filled bands that allow electrons to respond easily to fields, producing current. Insulators have gaps that block low-energy motion, preventing conduction. Devices work by shaping which states are available, and by controlling how electrons move between them. The visual world of modern electronics is a landscape of engineered constraints. Layers of silicon are doped with impurities, creating regions where electrons are abundant or scarce. At junctions, electric fields form barriers and wells, guiding carriers like invisible topography. The behavior is quantum at its foundation, even when the device looks classical at human scale. A transistor is, in part, a gatekeeper of electron states. Quantum tunneling is another refusal to sit still, and it is essential in modern devices. An electron can cross a barrier even when classical energy is insufficient, because its wave function extends into forbidden regions. The probability depends on barrier width and height, and it can be engineered with nanometer precision. Tunneling enables scanning tunneling microscopes, tunnel diodes, and parts of modern memory technologies. It also sets limits, because unwanted tunneling can become leakage in tiny circuits. A scanning tunneling microscope offers a particularly vivid image. A sharp tip hovers a fraction of a nanometer above a surface, and a small voltage is applied. Electrons tunnel across the gap, creating a current that depends exponentially on distance. By scanning the tip and keeping the current constant, the instrument maps the surface with atomic scale resolution. It is a machine that turns quantum probability into a picture. At this point, the electron begins to look less like an object and more like a manifestation. The theory that best unifies particles and interactions is quantum field theory. In that framework, the electron is an excitation of an electron field that fills space. The photon is an excitation of the electromagnetic field. Particles become quanta of fields, and interactions become couplings between those fields. Fields are not just mathematical conveniences in this view, they are the underlying entities, and particles are quantized disturbances in them. The electron field can be excited into a single electron, or many electrons, and the excitations carry the same charge and mass. Identity becomes a property of the field, not of a tiny pellet. That is why every electron is indistinguishable from every other electron down to the limits of measurement. This reframes what empty space means. Even in a perfect vacuum, fields remain present, and quantum rules allow fluctuations. Vacuum fluctuations are not a free energy source, but they can shift measurable quantities. They contribute to effects like the Lamb shift in hydrogen and the Casimir force between plates. The vacuum is not a void, but a structured baseline that can be perturbed. The Lamb shift is a useful reminder that the electron's environment is never perfectly simple. In hydrogen, energy levels that would be identical in a simpler theory are slightly split. The shift arises from interactions between the electron and the fluctuating electromagnetic field, including vacuum polarization and self-energy effects. The difference is tiny, but it is measurable, and it matches quantum electrodynamics with extraordinary precision. Small corrections become a window into deep structure. the vacuum becomes a subtle background that is never truly blank. It can polarize in the presence of charges, altering effective interactions. It can briefly host virtual particle pairs within quantum limits, changing how fields propagate. These effects are small, but they are precise, and they reveal that emptiness has structure. The electron, even alone, is never completely alone because it sits in a sea of fields. The electron's mass and charge also hint at deeper questions. Why does the electron have the mass it has, and why is its charge exactly equal and opposite to the protons? The Standard Model encodes these facts, and experiments confirm them with extreme precision. Yet the values still feel like inputs, not consequences, and the mystery remains. The theory tells us how the electron behaves, but it does not fully explain why its parameters take their particular numbers. Now widen the frame to cosmic context, because electrons are not local to laboratories. In the early universe, electrons were abundant in a hot plasma with photons and nuclei. Free electrons scattered photons efficiently through Thomson scattering, keeping the universe opaque. Radiation and matter were tightly coupled through constant interaction, like a fog so thick that light could not travel far. The cosmos was bright, but it was not transparent. As expansion cooled the plasma, a threshold was crossed. Electrons could bind to nuclei, forming neutral atoms, mostly hydrogen and helium. This recombination reduced scattering dramatically, allowing photons to travel long distances. The universe became transparent, and light could finally stream freely. In a sense, the universe acquired a surface, because we can see back to the moment when photons last scattered. Those freed photons are still here as the cosmic microwave background. Their spectrum is a cooled blackbody, stretched by expansion into microwaves, and it fills space in every direction. Their tiny anisotropies record early density variations, which later grew into galaxies and clusters. The timing of recombination depends on atomic physics, including electron binding energies and photon densities. Electron behavior helped set the moment the universe became readable. Electrons also shaped later cosmic chemistry and structure formation. Neutral gas could cool, collapse, and form stars more effectively than ionized plasma, because atoms and molecules can radiate energy away through quantized transitions. In stars and nebulae, electron transitions produce emission and absorption lines that reveal composition and motion. The same quantized steps that build chemistry also build astronomical diagnostics. When astronomers read spectra, they are reading electron energy levels written in light. Look at a nebula through a telescope, and the colors are not merely aesthetic. The reds and greens come from specific atomic transitions, often in hydrogen and oxygen, excited by nearby hot stars. Each line is a signature of electron rearrangement, a precise frequency that can be shifted by motion through the Doppler effect. From those shifts we infer winds, rotations, and expansions across light years. The electron becomes a messenger, carrying local physics into distant observation. So the electron connects the smallest and the largest scales in a single chain. It governs bonding and materials, and it also governs opacity and transparency in cosmic history. It is a particle we can count, and a wave we must accept, and an excitation of a field in deeper theory. Each layer answers a question and opens another. The deeper we go, the more the electron looks like a rulebook made tangible. The chapter's tension is that the electron is both accessible and unreachable. We can trap single electrons in electromagnetic fields and measure their properties with astonishing control. In penning traps, for example, electric and magnetic fields can find charged particles for long times, letting us probe their frequencies and magnetic moments. We can image electron density indirectly through scattering and spectroscopy, turning patterns of deflection into maps of structure. Yet we cannot demand a classical path without destroying the very interference that proves the wave aspect. There is a philosophical edge to that limitation. If the electron does not carry a definite path between events, what does it mean to say it went anywhere at all? Quantum mechanics answers with a pragmatic clarity. It tells us how to compute probabilities for outcomes, given a preparation and a measurement. It does not always grant a narrative of motion that matches our everyday storytelling. The electron forces us to separate explanation from visualization. This is where the documentary's central question sharpens again. If matter is built from particles, those particles behave like probabilities. If forces are exchanges, the exchange particles are also quanta of fields. The smallest things are not tiny objects alone. They are interactions, constraints, and excitations that only look like objects in certain measurements. The electron is a lesson in how the universe can be both discrete and wave-like without contradiction. We end with the next step already implied by the electron's behavior. Electrons exchange something to create forces, and that something is tied to light. Photons appear both as waves and as particles, and they carry the electromagnetic interaction itself. If electrons talk by exchanging photons, then we have to follow the messenger. The next chapter turns from the restless electron to the equally strange carrier that makes its interactions possible. If the electron refuses to sit still, the photon refuses to be only light. The next chapter follows that exchange and asks why the force carrier is also the thing we see as illumination. The mystery tightens because the same quantum rules that blur electrons also define what a photon can be, and once we understand the messenger, we may see that the message is the fabric of reality itself, written in quanta and delivered as light. Light feels familiar because it fills our days, yet it carries the strangest rules we know. It pours through windows, glints off water, and paints shadows that seem perfectly ordinary. Yet behind that comfort sits a framework that resists common sense, even when the math stays simple. In earlier chapters, electrons refused classical paths and forced probability into the story. We watched matter behave like a spread of possibilities, not a tiny marble with a trackable route. Now we follow what electrons exchange and what our eyes receive. The photon becomes both messenger and evidence, because nearly everything we know about the universe arrives as light. Start with the classical picture, because it is still partly true. Light behaves like a wave in space, with wavelength, frequency, and phase. In a visualization, you can imagine ripples moving outward, crest after crest, carrying energy without carrying material. The wave's rhythm sets the color we perceive, even though color is only our brain's label. A wavelength is a distance between repeating peaks, while frequency is how often those peaks pass a point. The two are tied together by the speed of light, so changing one forces the other to shift. Phase is subtler, because it tracks where you are inside the wave's cycle at a given location. Phase is the hidden clock that decides whether waves cooperate or fight. Waves add and cancel, and that simple rule creates interference patterns. When two paths meet, brightness and darkness appear as geometry made visible. On a screen, the pattern looks like a barcode of light, as if the wave is drawing a measurement of its own timing. Interference is not a metaphor in physics, it is a measurable accounting of phase. Two waves arriving in step reinforce, while two waves arriving half a cycle apart erase. The mathematics is straightforward, but the consequences feel almost theatrical. Light can create darkness by addition. A double-slit setup turns that accounting into a pattern of bands. A bright central stripe forms where path lengths match, then alternating bright and dark fringes spread outward. The spacing depends on wavelength, slit separation, and distance to the screen. Change the path difference, and the bands shift predictably. Classical waves explain this with ease, and that ease is part of the trap. The explanation feels complete because it matches what the eye sees. It also matches what antennas do with radio waves, and what water does in a tank. The trouble begins when we ask how light trades energy with matter. Polarization adds a second wave feature that looks purely continuous. Light has an electric field direction, and filters can select one orientation. In a visual diagram, the wave is not just up and down, but also angled, like a vibrating string rotated in space. Polarization is the wave's internal orientation, carried along with its motion. Rotate a polarizer, and intensity follows a cosine-squared rule. The transmitted brightness fades smoothly, as if the wave is being projected onto a preferred axis. Two crossed polarizers block light, yet a third between them can restore transmission. The middle filter rotates the allowed direction step by step, revealing that blocked is not always final. These wave behaviors are real, but they are not the whole story. The first crack appears when light trades energy with matter. Heat a metal, shine light on it, and electrons can be ejected. The details refuse classical expectations, and the refusal is precise. By the late 19th century, physicists had become confident in waves and fields. Maxwell's equations unified electricity, magnetism, and optics into a single elegant structure. Light looked like the triumph of continuity, a smooth field undulating through space. Then, experiments began to show that smooth waves were not enough. The photoelectric effect shows that brightness is not the key variable. Below a threshold frequency, no electrons are emitted no matter how intense the light. Above that threshold, electrons appear immediately, even at low intensity. Increase frequency, and the electron kinetic energy increases linearly. That immediacy matters, because classical waves suggest a different story. If energy arrives continuously, a dim light should still eject electrons given enough time to soak them with energy. Yet the electron does not wait, and it does not accumulate energy gradually. It either leaves at once, or it never leaves. This is where quantization stops being optional. Planck introduced energy quanta to explain blackbody radiation, where hot objects emit light with a spectrum that classical physics mispredicted. He treated energy exchange as occurring in discrete steps, a mathematical fix that worked too well to ignore. Einstein then applied the idea to light itself, turning a trick into a statement about reality. Light arrives in packets with energy E equals h times f. The constant h, Planck's constant, is small, which is why quantization hides in everyday life. But at the scale of atoms, h sets the size of the steps, and the steps become unavoidable. The photon is not a wave chopped into pieces, it is a quantum of the electromagnetic field. The photon concept explains the threshold cleanly. An electron needs a minimum energy to escape the metal, called the work function. One photon gives one electron one chance, and the energy must be enough. Intensity changes the number of photons, not the energy per photon. In practice, the work function depends on the material and its surface condition. Different metals hold their electrons with different binding energies, shaped by electron bands and atomic structure. Even a thin layer of contamination can shift the threshold, which is why careful experiments polish and clean surfaces. The threshold is not a vague boundary, but a material fingerprint. The linear relation between frequency and electron kinetic energy became a straight line on a graph. Its slope is Planck's constant, pulled from data like a signature. The intercept gives the work function, turning a mysterious effect into a measurable equation. A single experiment links light's colour to a fundamental constant of nature. Compton scattering extends the evidence into momentum. X-rays collide with electrons and emerge with longer wavelength. The shift depends on scattering angle in a way that matches particle kinematics. Light carries momentum p equals h over lambda, and momentum exchange is measurable. The Compton effect is especially striking because it treats light like a billiard ball. A photon comes in with a certain wavelength, hits an electron, and leaves with a different wavelength. The electron recoils, carrying away energy and momentum. The wavelength shift is not arbitrary, but fixed by geometry and conservation laws. This is not a minor correction to wave theory, but a new kind of bookkeeping. The photon behaves as if it has a momentum vector, even though it has no rest mass. The collision looks like a particle event, localized in space and time, yet the photon still diffracts and interferes like a wave. So photons have wave signatures and particle signatures, and neither can be discarded. The wave description predicts interference and polarization with high accuracy. The particle description predicts discrete energy transfer and momentum kicks with equal accuracy. The paradox is not that we lack models, it is that both models are required. Historically, this was not a smooth transition. The early 20th century was a period of conceptual whiplash, when each new experiment forced a new compromise. Some physicists tried to keep waves and treat matter as quantized, while others tried to keep particles and quantize fields. The photon became the place where the argument could not be postponed. Single photon experiments make the tension unavoidable. Send photons one at a time through a double-slit apparatus. Each detection is a localized click, never a smeared wave on the screen. Yet the accumulated clicks form an interference pattern, as if each photon interfered with itself. Visually, the screen begins almost empty, with only a few scattered points. Then more points arrive, and faint stripes begin to emerge from apparent randomness. After thousands of detections, the interference pattern becomes crisp, as if an invisible stencil had been guiding every arrival. The pattern is statistical, but it is not optional. The pattern depends on what information is available in the apparatus. If the setup records which path the photon took, interference disappears. If path information is erased or never created, interference returns. The outcome is not about human awareness, it is about physical entanglement and information. What counts as which path is not a philosophical trick but a physical condition. If the photon leaves a trace in the environment, even a subtle one, the paths become distinguishable. That trace can be a scattered photon, a vibration, or a microscopic change in a detector. When paths become distinguishable, the interference term is suppressed. Here, measurement becomes a narrative engine rather than a footnote. Quantum mechanics predicts probabilities for outcomes, given a preparation and a measurement. It does not always assign a single history between emission and detection. The photon forces us to separate what we can predict from what we can claim happened. In the wave language, we compute amplitudes, and we add them before squaring. Those amplitudes can cancel, which is why interference produces darkness. In the particle language, we count clicks, and the clicks arrive one at a time. Quantum theory insists that both descriptions are part of one consistent framework. Collapse is the name we give to the moment a spread of possibilities becomes one recorded event. In practice, we see it as a detector click and a stored bit. In theory, we track it as an update from amplitudes to outcomes. The documentary tension is simple and persistent. The universe offers exact statistics, yet withholds a classical story. We can predict the distribution of outcomes with extraordinary accuracy. We cannot always narrate a single observer-independent path that the photon really took. The photon makes that absence feel personal, because light is how we see. Photon basics anchor the rest of the chapter. Photons have zero rest mass and no electric charge. In vacuum, they always move at c, the same speed for all observers. Their energy is tied to frequency, and their momentum is tied to wavelength. That constant speed is not merely a property of light, but a structural feature of space-time. It appears in relativity as the conversion factor between time and distance. When we say photons always move at c, we're also saying that the geometry of the universe sets a universal limit. Light is not just a traveller, it is a ruler. Because photons carry momentum, light can push matter. Radiation pressure is small in daily life, yet it is real and measurable. It shapes comet tails, drives stellar winds, and can cool atoms in laser traps. In space, where friction is absent, even tiny pressure can accumulate into motion. A comet's tail is a vivid demonstration, drawn across the sky like a brushstroke. Dust and gas stream away from the nucleus, and the tail points away from the sun. Part of that push comes from the solar wind, but part comes from sunlight itself. Photons arrive, deliver momentum, and depart. An invisible rain with a gentle force. In laboratories, radiation pressure becomes a tool rather than a curiosity. A laser beam can slow atoms by repeated absorption and emission, each photon delivering a small kick. Over many cycles, those kicks reduce atomic motion, effectively lowering temperature. The atoms do not cool because they feel cold, but because their kinetic energy is reduced. Photon momentum also explains why atoms recoil when they emit or absorb light. Emission is not only an energy change, it is a momentum exchange. Recoil shifts spectral lines by tiny amounts that precision instruments can detect. Even in the simplest atom, light and matter share bookkeeping. This recoil is usually minuscule, yet it matters in high-precision spectroscopy. When an atom emits a photon, the atom must move slightly in the opposite direction to conserve momentum. That motion changes the photon energy by a small amount, a shift that can be calculated. The details remind us that conservation laws do not negotiate. To move from quantum mechanics to deeper structure, we shift language from particles to fields. In quantum field theory, the electromagnetic field is fundamental. A photon is an excitation of that field with quantized energy and momentum. The field is not a medium like air. It is a set of values defined everywhere in space. That distinction is easy to miss because field sounds like something that fills space like a substance. But the electromagnetic field is not a material ether, and it does not require a preferred rest frame. It is a mathematical object that assigns potential and field strengths to each point. In quantum theory, those values become operators, and excitations become quanta. This framing clarifies why photons are identical. Every photon is an excitation of the same underlying field, distinguished only by quantum numbers like frequency, direction, and polarization. Identity becomes a property of the field, not of a tiny object with a hidden label. The photon is a repeatable pattern, not a unique bead. In visuals, you might imagine the field as a dark ocean that can support quantized ripples. Each ripple carries a precise amount of energy and momentum, and you cannot create half a ripple of the allowed kind. The ocean is everywhere, even in empty space, and the ripples are what we call particles. The metaphor is imperfect, but it points in the right direction. Quantum electrodynamics is the most precise theory in physics, and photons are its central actors. QED describes how charged particles interact by emitting and absorbing photons. It predicts scattering rates, atomic energy shifts, and magnetic moments with astonishing accuracy. Its success is a clue that the field picture is not just convenient. One famous example is the electron's magnetic moment, which QED predicts to many decimal places. The agreement between theory and experiment is so tight that it feels like a stress test of reality. Tiny corrections come from virtual processes, calculated as series expansions. When the numbers match, it is hard to argue that photons are merely a metaphor. In QED, electromagnetic forces can be described as exchange of virtual photons. Virtual photons are not directly detected particles travelling to a screen. They are internal terms in the calculation that represent allowed intermediate processes. They can violate the free particle energy momentum relation within quantum limits because they are not on shell. The phrase virtual photon can mislead because it sounds like a ghost particle flying between charges. A better image is a set of allowed transitions that contribute to a probability amplitude. The virtual photon is part of the accounting, not a recorded event. Yet the accounting predicts measurable forces, which is why the language persists. This is why electromagnetism can act across distance without a classical medium. The interaction is encoded in field correlations and exchange amplitudes. The diagrams are bookkeeping, yet the bookkeeping predicts real numbers. Forces become conversations in quanta, and the photon is the grammar. Those diagrams, Feynman diagrams, also carry historical weight. They turned forbidding integrals into pictures that guided intuition, without replacing the mathematics underneath. Lines and vertices became a visual shorthand for terms in an expansion. The photon line is not a literal path, but it is a reliable guide to what contributes. The vacuum itself becomes active in this view. Fields fluctuate, and those fluctuations shift measurable quantities. The Lamb shift in hydrogen is one famous consequence. The Casimir force between plates is another. Empty space is not nothing. It is a structured baseline with quantized degrees of freedom. Even when no real photons are present, the electromagnetic field has a ground state with fluctuations. Those fluctuations can polarize atoms slightly and alter energy levels. The vacuum becomes a participant, not a backdrop. Now we widen into the experimental toolkit, because photons are how we interrogate the invisible. Detectors turn photon arrivals into electrical signals, one event at a time. Photomultiplier tubes, avalanche photodiodes, and superconducting sensors can register single photons. The click becomes the unit of evidence. A photomultiplier tube turns one photon into a cascade of electrons. The photon strikes a photocathode, releasing an electron that is accelerated into a dinode chain. Each impact releases more electrons, amplifying the signal until it becomes measurable. The device is like a controlled avalanche, engineered for sensitivity. Avalanche photodiodes use a similar principle in semiconductor form. A photon creates a charge carrier, and a strong electric field multiplies it through impact ionization. The result is a pulse that can be timed with high precision. Timing matters because it lets us reconstruct events, not just count them. Superconducting sensors push sensitivity even further. At very low temperatures, a photon can break Cooper pairs and change electrical properties measurably. These detectors can resolve photon energy and arrival time with remarkable fidelity. The cost is complexity, because the apparatus must be colder than deep space. Spectroscopy is the most powerful photon-based inference tool we have. Atoms and molecules absorb and emit at discrete frequencies. Those frequencies encode energy level differences and selection rules. By measuring lines, we identify composition, temperature, density, and motion, even across interstellar distances. A spectrum is a coded message, spread out by a prism or a grating. Dark absorption lines cut into a bright continuum, while bright emission lines stand out against darkness. Each line corresponds to a transition, and each transition obeys quantum rules. The pattern is not artistic. It is constrained by angular momentum and symmetry. Motion leaves its mark through the Doppler shift. If a source moves toward us, its lines shift to shorter wavelengths, and if it moves away, they shift longer. That shift becomes a speedometer for stars and galaxies. With enough precision, it can reveal orbiting planets through tiny wobbles. Scattering is the logic that connects photons to unseen structure, shine light, X-rays, or gamma rays on matter, and measure angles and energies after interaction. The pattern reveals size scales, charge distributions, and internal dynamics. From Rutherford to modern colliders, scattering is how we see without seeing. The core idea is simple. The way a beam changes tells you what it hit. Small-angle scattering reveals large structures, while wide-angle scattering probes small distances. Energy loss can reveal internal excitations, and polarization changes can reveal anisotropy. Each measured photon becomes a clue in a reconstruction. Different photon energies probe different scales. Radio waves map large structures and cold gas through long wavelengths. Visible and ultraviolet probe electronic transitions and hot plasmas. X-rays probe inner shells and high-energy environments. Gamma rays probe nuclear processes and extreme cosmic accelerators. These windows are not equally transparent. Earth's atmosphere blocks most ultraviolet, X-rays and gamma rays, which is why space telescopes are necessary. Radio and visible light reach the ground, shaping the history of astronomy. The spectrum is a landscape, and we explore it with instruments tailored to each region. The same logic applies to electrons and to photons, but photons have a special role. They travel long distances without easily being absorbed, especially in transparent windows of the spectrum. They carry information across the universe with minimal distortion. They are the messengers that survive the trip. That survival makes photons the documentary's narrative thread. We infer atoms from spectral lines, electrons from scattering and emission, and fields from subtle shifts. We reconstruct events we never witnessed by reading the photons that remain. The photon is evidence, not just illumination. Now the cosmology centerpiece arrives, because the oldest light is still with us. The early universe was a hot plasma of electrons, nuclei, and photons. Photons scattered constantly off free electrons, keeping the universe opaque. Light existed everywhere, yet it could not travel far. If we could visualize that era, we would not see stars or galaxies. We would see a glowing fog, dense and bright, where every photon was quickly deflected. The mean free path of light was short because free electrons were abundant. The universe was luminous and blind at the same time. As expansion cooled the plasma, electrons bound to nuclei and formed neutral atoms. This epoch is recombination, and it changed the universe's transparency rapidly. With fewer free electrons, scattering dropped, and photons began to stream freely. The universe gained a visible surface, defined by the last scattering of light. The term recombination is slightly misleading, because electrons and nuclei were combining for the first time. The key is that neutral atoms do not scatter light as strongly as free electrons do at those energies. Once neutrality arrived, the fog lifted. A photon could finally travel, carrying a snapshot of conditions at that moment. Those photons still fill space as the cosmic microwave background. Expansion stretched their wavelengths into microwaves, cooling the spectrum into a near-perfect blackbody at about 2.7 Kelvin. The CMB is not a picture of galaxies, it is a fossil of conditions before stars existed. It is the earliest electromagnetic message we can read directly. The blackbody shape is important because it signals thermal equilibrium in the early plasma. The spectrum's smooth curve is not a random assortment of colours. It is the statistical distribution expected from a hot, dense environment, where photons were repeatedly absorbed and re-emitted. When the universe became transparent, that distribution froze in place and then redshifted. The CMB is astonishingly uniform, and that uniformity is itself a clue. Yet it contains tiny anisotropies at the level of tens of microkelvin. Those variations map density ripples in the early universe. They are the seeds that later grew into galaxies and clusters under gravity. On a CMB sky map, the variations look like mottled colour patches spread across a sphere. The colours are not artistic, but scaled to reveal differences that are otherwise invisible. Each patch corresponds to a region that was slightly hotter or slightly cooler at last scattering. Slightly hotter often means slightly denser, because gravity and compression affected temperature. Anisotropies also encode acoustic physics in the primordial plasma. Gravity tried to compress over dense regions, while radiation pressure pushed back. The competition created sound waves in the photon-baryon fluid. The angular power spectrum of the CMB records those oscillations as peaks, and the peak positions constrain cosmological parameters. Those peaks are a kind of cosmic fingerprint. Their spacing depends on geometry, because geometry controls how physical sizes project onto angles in the sky. Their heights depend on matter content, because matter changes how strongly the plasma oscillated. A plot of peaks becomes a compressed history of the early universe's ingredients. Polarization in the CMB adds another layer of information. Thomson's scattering of photons off electrons produces polarization patterns. E-modes trace density perturbations and velocity flows at last scattering. B-modes, if primordial, would hint at gravitational waves from inflation, though foregrounds complicate the search. Polarization is subtle because it is a pattern in the orientation of light, not its brightness. It arises when scattering sees a quadrupole anisotropy in the incoming radiation. The result is a faint directional imprint across the sky. Measuring it requires exquisite control of systematic errors, because the signal is small and the foregrounds are loud, so the CMB is not just old light, it is a precision data set. It tells us the universe's age, geometry, and matter content. It constrains the baryon density and the dark matter fraction. It links atomic physics to cosmic structure, because recombination depends on electron binding and photon density. The link is almost poetic because it ties the hydrogen atom to the shape of the cosmos. The energy levels of hydrogen determine how and when electrons bind. That timing determines when photons decouple and begin free streaming. Those photons then become a map we can measure billions of years later. Photons also connect microphysics to cosmic evolution through starlight. Stars shine because nuclear fusion converts mass into energy. That energy emerges as photons after many interactions inside stellar plasma. By the time photons escape a star's surface, they carry a spectrum shaped by temperature and atomic absorption. Inside a star, a photon's journey is slow and indirect. It is absorbed and re-emitted countless times, changing direction like a random walk. Energy moves outward not as a single photon's straight flight, but as a diffusion process through dense plasma. The sunlight that reaches Earth began as high-energy radiation deep within, then was transformed and thermalized. Element formation leaves distinct photon signatures. Hydrogen fusion produces neutrinos and gamma rays deep inside, then thermal photons at the surface. Heavier element synthesis in massive stars changes opacity and spectral lines. Supernovae create heavy nuclei and release bursts of light that reveal nucleosynthesis in real time. When a supernova erupts, the light curve rises and falls with a characteristic shape. That shape reflects radioactive decay chains and the expanding debris' transparency. Spectra taken over days show lines shifting and evolving as different layers become visible. The explosion is not just a flash, but a time-resolved laboratory. Spectral lines in starlight show which elements are present. Iron lines, calcium lines, and molecular bands become evidence of stellar composition and evolution. Metallicity measurements trace generations of star formation across galaxies. Photons become a chemical census, linking nuclear reactions to the material that later forms planets. Even the absence of lines can be informative, because it can indicate extreme temperatures or ionization states. In very hot stars, atoms are stripped of electrons, changing which transitions are allowed. In cool atmospheres, molecules form and produce broad bands. The spectrum becomes a thermometer and a chemistry report at once. Even dust and gas clouds announce themselves through photons. Infrared emission reveals warm dust heated by starlight. Radio lines from neutral hydrogen map galactic structure through the 21 centimeter transition. Molecular lines trace cold star-forming regions where new suns ignite. The universe is read in frequencies, not in direct touch. The 21 centimeter line is especially evocative because it comes from a subtle flip in hydrogen's spin configuration. It is a weak transition, but hydrogen is abundant, so the signal accumulates. Radio telescopes translate that faint whisper into maps of spiral arms and interstellar clouds. A single quantum transition becomes a galactic cartography tool. The photon story also reveals limits and biases in what we can know. Some regions are opaque at certain wavelengths, hiding behind absorption. Some epochs are beyond electromagnetic reach, because before recombination the universe was effectively fogged by scattering. Photons carry information, but they also mark the boundary of visibility. That boundary invites a quiet question. How much of our cosmic story is shaped by what light can carry, rather than what exists? We build narratives from what reaches us, and photons decide what reaches us. The messenger shapes the message, even when we try to be objective. This boundary sharpens the central question of the documentary. What is everything made of, if our best evidence arrives as quanta of a field? Matter is not only particles, it is interactions mediated by exchange quanta. The photon is not just a carrier, it is part of what matter is doing. We return to wave-particle duality with a more mature framing. The photon is not sometimes a wave, and sometimes a particle in a naive sense. It is a quantum object described by a state, with outcomes that depend on measurement context. Interference is about amplitudes, and detection is about discrete energy exchange. In this view, the paradox becomes a tool rather than a dead end. We use interference to measure phase and distance with extreme sensitivity. We use polarization to encode and filter information. We use photon counting to reach quantum limits of measurement. The same strangeness that confuses intuition also powers modern technology. Interferometers can detect minute changes in length by watching fringes shift. A tiny phase change becomes a measurable change in brightness. Polarization optics can separate signals from noise by selecting specific orientations. Photon statistics can reveal whether light is thermal, coherent, or truly quantum. Quantum optics turns photons into engineered resources. Lasers create coherent states with well-defined phase relationships. Single photon sources and entangled pairs enable tests of non-local correlations. Bell experiments show that no local hidden variable theory can reproduce quantum predictions. Photons become carriers of entanglement, not just carriers of energy. In a Bell test, two photons fly apart to distant detectors, and their polarization measurements show correlations. The correlations violate inequalities that any local classical model must satisfy. The result is not a loophole in arithmetic, but a constraint on how reality can be organized. Something about the world is non-classical at a deep level. Entanglement also reframes what information means in physics. Correlations can be stronger than classical expectations, yet they do not allow faster-than-light signaling. The photon becomes a messenger whose message is constrained by quantum rules. Information is physical, but it is not free to break causality. This balance is delicate and revealing. Quantum mechanics permits correlations that feel instantaneous, yet it preserves the impossibility of sending controlled messages faster than light. The randomness of outcomes protects causality, even as the correlations defy classical explanation. The photon carries mystery, but it also carries discipline. The measurement problem remains as a controlled mystery. We can calculate outcomes with extraordinary precision, yet we still debate what the wave function represents. Is it knowledge, physical reality, or a bookkeeping device for correlations? The documentary does not need a final verdict, because the tension itself is historically productive. Different interpretations offer different stories, but they share the same predictions. Some emphasize branching worlds, others emphasize hidden variables, and others emphasize information updates. What remains constant is the experimental record, the clicks, the fringes, the thresholds. The photon keeps the debate grounded in data. Now we tighten the thread back to matter. Photons reveal atoms through spectra, and electrons through scattering. They also mediate the electromagnetic force that shapes chemistry and solidity. Yet photons do not explain why nuclei hold together against electric repulsion. The photon carries a force, but not the force that binds protons in the nucleus. Electromagnetism builds the outer architecture of matter. It sets the shapes of electron orbitals, the strength of chemical bonds, and the rigidity of solids. It explains why atoms form molecules and why materials conduct or insulate. But when we look into the nucleus, the same force becomes a problem, because like charges repel. This is the transition point where the messenger points beyond itself. Electromagnetism can probe nuclei with high energies, yet it does not supply the binding glue. The next layer is deeper, denser, and ruled by a force that does not reach far. The photon can illuminate the boundary, but it cannot cross it alone. We end with a question that light cannot answer by itself. Photons can tell us what atoms are doing and what electrons allow. They can even show us the universe's first transparent moment in the CMB. But the nucleus remains a compact mystery at the center of every atom. Photons reveal atoms and electrons, but the nucleus holds a deeper secret. what keeps it together, and what is a neutron really? The descent continues, and the next chapter follows that question into the heart of matter. We have followed atoms outward through electrons and photons, then back inward toward the core, and the scale change is almost obscene. The nucleus is the atom's locked room, tiny in volume and immense in consequence, and it forces physics to speak in a different accent. It holds nearly all atomic mass, and it sets the identity of every element, because chemistry can shuffle electrons but cannot rewrite proton count. It also poses an immediate contradiction that classical intuition cannot ignore, because the same laws that explain sparks and magnets appear to forbid the nucleus itself. A nucleus is built from nucleons, protons and neutrons packed into femtometer scales, where a femtometer is a millionth of a billionth of a meter. Picture a cathedral-sized atom reduced to a stadium, and the nucleus becomes a marble at the centre. Yet it contains almost everything that matters. If the atom were the size of a city block, the nucleus would be a grain of dust, and the electrons would still be far away. Protons carry positive charge, so they repel each other through electromagnetism, and that repulsion is not subtle at these distances. At nuclear separations, the Coulomb force becomes fierce, and it should drive protons apart with a violence that seems unavoidable. If electromagnetism were the only rule, complex nuclei would not exist for long, and the periodic table would collapse into a lonely hydrogen universe. Yet nuclei do exist, and most are stable over cosmic time, which means the contradiction is only apparent. The reason is not a clever arrangement of charges, or a hidden electromagnetic trick, or some geometric loophole that lets protons miss each other. A different interaction dominates at short range, and it does not behave like light, because it does not stretch smoothly across space. The strong interaction is the glue that can overpower repulsion, but only inside a very small radius. Outside that radius, it fades so quickly that, for ordinary chemistry, it might as well be absent. In practice, it is an interaction with a steep edge. Over a couple femtometers, it goes from overwhelming to irrelevant. Start with the simplest nuclei to anchor the scale, because the smallest cases reveal the rules without distraction. Hydrogen's most common form is a single proton, with no neutrons at all, and that simplicity is deceptive because it is already a composite particle. Even that lone proton is not a point, because scattering shows a finite charge radius and internal motion. Deuterium adds one neutron, and the pair becomes bound as a deuteron, a fragile but real nucleus with a binding energy of only a few million electron volts. That binding is weak enough that thermal collisions in stars can break deuterons apart, which is why early fusion must fight both heat and chance. Helium-4 packs 2 protons and 2 neutrons into a tightly bound state, and its stability is so pronounced that it appears again and again in nuclear reactions. The binding energy per nucleon rises quickly from hydrogen to helium, and that curve is a fingerprint that something powerful is at work. Binding energy is not an abstract bookkeeping trick, because it is literally missing mass. When nucleons bind, the nucleus weighs slightly less than the sum of its parts, and the difference appears as energy through E equals mc squared. That mass defect is small in everyday units, yet it is enormous on an atomic scale, and it is why nuclear processes can outshine chemical ones. A chemical bond rearranges electrons and trades energy in electron volts, while a nuclear bond trades energy in mega electron volts. The nucleus is not just smaller than the atom, it is a different regime of power. When you translate that difference into heat, light and radiation, it becomes the difference between a flame and a star. The strong force is not just electromagnetism with a bigger number, and the difference is not merely intensity. Electric forces weaken smoothly with distance, and they can be screened by opposite charges, which is why conductors can hide fields inside. The strong force is short-range, saturating, and largely indifferent to electric charge, which means it does not care whether a nucleon is a proton or a neutron. It binds protons to protons, neutrons to neutrons, and protons to neutrons with comparable strength. Though subtle spin and isospin details matter, it also becomes repulsive at extremely short distances, preventing nucleons from collapsing into a point, a hardcore behavior that keeps nuclei from becoming singular. That repulsive core is one reason nuclei have a characteristic density, almost constant across elements, as if nuclear matter has its own preferred packing. This short-range behavior creates the locked room feeling, because the nucleus is both isolated and intense. Outside the nucleus, the strong force is almost invisible, and chemistry never notices it, even though chemistry builds everything we touch. Inside the nucleus, it dominates everything, and electromagnetism becomes a secondary complication that must be managed rather than obeyed. The same atom that feels mostly empty at angstrom scales becomes crowded and violent at femtometer scales, like stepping from a quiet hallway into an engine room. If you could slow time and watch, nucleons would not sit still, because quantum motion keeps them in restless overlapping states. The documentary's central question tightens here, because matter's stability depends on rules we cannot see directly, and on balances that look precarious even in theory. Neutrons enter the story as stabilizers, but they are not passive fillers wedged between protons like packing foam. A neutron has no net electric charge, so it does not add Coulomb repulsion, and that neutrality is a strategic advantage in a charged crowd. Its mass is close to the protons, slightly heavier, so it contributes to nuclear mass without changing charge, which is why isotopes can vary in weight while remaining the same element. Neutrons add strong force attraction without adding electric pushback, which helps nuclei hold together as proton number grows. In heavier nuclei, the neutron-to-proton ratio must rise, because extra neutrons are the price of keeping many protons in one room. The trend is visible across the chart of nucleids, where stable isotopes bend toward neutron richness as charge climbs. But neutron neutrality does not mean neutron simplicity, and the word neutral can mislead. Neutrons have internal structure and magnetic moments, and they participate fully in strong interactions, which means they are not inert spectators. Their magnetic moment reveals moving charges inside, a clue that the neutron is built from charged constituents whose effects cancel overall. Neutrons also change the balance of quantum states inside the nucleus, because the nucleus is not a classical pile of marbles. Like electrons in atoms, nucleons are fermions, and they obey exclusion rules that forbid identical quantum states from being shared. That rule forces a kind of internal architecture, where available states fill in an ordered way, even when the nucleus looks like a simple lump. That exclusion principle creates nuclear shells and pairing effects, which are the nucleus's version of electron orbitals, though the underlying potential is different. The shell model emerged in the mid-20th century, and it was a turning point because it explained why certain nuclei are conspicuously stable. Certain numbers of protons or neutrons fill shells in a way that makes the nucleus unusually stable, producing the so-called magic numbers that recur across the chart of nucleides. Pairing matters too, because nucleons like to form spin-coupled pairs, and nuclei with even numbers of protons and neutrons tend to be more stable. These patterns are not decorative, they shape which isotopes exist naturally and which must be manufactured in accelerators. The nucleus is a quantum system first, and a cluster of particles only as a useful approximation. Isotopes reveal the neutron's role with clarity, because they let us change one variable while holding the other fixed. The element is defined by proton number, but isotopes vary by neutron number, and that variation can transform stability without changing chemistry. Carbon-12 and carbon-14 share 6 protons, yet their stability differs dramatically, and the difference echoes through biology and geology. Carbon-12 is stable, while carbon-14 decays with a half-life of about 5,630 years, a span long enough to matter for humans and short enough to be measurable. The difference is not chemistry, but nuclear bookkeeping, a quiet imbalance in the locked room. When you hold a piece of charcoal or a bone fragment, you're holding a statistical clock that began ticking when the organism stopped exchanging carbon with air. Too few neutrons leaves protons insufficiently bound against repulsion, and the nucleus can become proton-rich and strained. Too many neutrons creates a different tension, because the nucleus must accommodate extra fermions in higher energy states, and those states cost energy. The strong force saturates, meaning each nucleon mainly binds to near neighbours, so the benefit of adding one more neutron eventually diminishes. Meanwhile, the quantum energy costs rise, because additional neutrons must occupy less favourable configurations and can distort the nucleus's shape. Stability becomes a narrow corridor, not a guaranteed outcome, and many isotopes live outside it only briefly. The corridor is sometimes called the Valley of Stability, and it is carved by competing terms in nuclear energy: surface effects, Coulomb repulsion, and the penalties of imbalance. Radioactivity is the sign that a nucleus is trying to escape that corridor, and it is also the signature that nuclear identity is not fixed. An unstable nucleus can shed energy, and reconfigure by emitting particles or radiation, and the mode of escape depends on what imbalance dominates. Alpha decay ejects a helium nucleus, reducing both proton and neutron counts, and it tends to occur in very heavy nuclei where Coulomb repulsion is overwhelming. Gamma decay releases photons, changing energy state without changing identity, like a bell ringing after being struck. Beta decay changes the identity itself, converting a neutron to a proton or a proton to a neutron, and it is the nucleus rewriting its own census. Each mode has its own signature in detectors, tracks, energies, and timing that let us read a hidden event. Historically, radioactivity was one of the first hints that atoms had internal structure at all, long before anyone could name quarks or gluons. In the late 19th century, Henri Becquerel noticed spontaneous emissions from uranium salts, and Marie and Pierre Curie pursued the phenomenon into new elements and new dangers. Ernest Rutherford distinguished alpha and beta radiation, and later used alpha particles as probes, linking decay to structure in a single arc of discovery. The early language was almost alchemical, because the idea of one element turning into another sounded like heresy against chemistry. What began as mysterious fogging on photographic plates became a map of nuclear transformations, and eventually a toolkit for measuring time. Beta decay is where time enters the nucleus as a measurable feature, because beta processes can be slow enough to watch. In beta minus decay, a neutron becomes a proton, emitting an electron and an antineutrino, and the nucleus moves toward a more stable neutron-to-proton ratio. In beta plus decay, a proton becomes a neutron, emitting a positron and a neutrino, which requires enough energy to create the positron's mass. Electron capture offers another pathway, where a proton absorbs an inner electron and becomes a neutron, leaving a vacancy that can produce characteristic X-rays. These processes are not driven by the strong force, but by the weak interaction, a different rulebook operating beneath the nuclear surface. The weak force is named for its strength, yet its consequences are immense, because it decides which imbalances can be corrected at all. The weak interaction is quieter than the strong force, yet it decides which nuclei can persist, and it does so with a kind of statistical patience. It allows flavor change among quarks inside nucleons, enabling neutron and proton conversion, and it is one of the few interactions that can change particle type. It also produces neutrinos, particles that escape almost without interaction, slipping through Earth as if it were thin mist. The nucleus can therefore change identity while barely disturbing its surroundings, because most of the energy and momentum can be carried away invisibly. Radioactivity becomes a clock because weak processes have characteristic probabilities per unit time, and those probabilities are stable across eras. The same decay law holds in a cave, in a laboratory, or in a meteorite drifting between planets. Half-life is the nucleus's way of expressing quantum chance, and it forces us to think in populations rather than individuals. A single nucleus does not carry a timer that counts down deterministically, as if it knew its own appointment with decay. It carries a decay probability, and the statistics become predictable only in large numbers, where randomness averages into law-like curves. This echoes earlier chapters where quantum mechanics predicts distributions precisely, but refuses a classical in-between story. Nuclear decay is a macroscopic, everyday example of that same rule, because a rock can be dated by the collective behavior of countless unstable nuclei. It is worth asking what kind of universe this is, where certainty emerges only when you stop looking at individuals. Those decay clocks let us measure deep time on Earth, and they also remind us that timekeeping can be built from instability. Uranium and thorium chains date rocks, anchoring the age of continents and the planet, and they do so through multi-step cascades with distinct daughter isotopes. Carbon-14 dates once-living material, tying nuclear physics to archaeology and climate history, and it works because cosmic rays continually replenish carbon-14 in the atmosphere. Potassium-40 and rubidium-strontium methods extend the range, mapping billions of years, and they are chosen because their half-lives match the ages we need. The nucleus becomes a timekeeper for geology, not by intention, but by quantum inevitability, an accidental chronometer embedded in matter. When we speak of Earth being ancient, we're really speaking the language of nuclei. The nucleus also records cosmic time, because elements carry origin stories that can be read in abundance patterns. Big Bang nucleosynthesis produced mostly hydrogen and helium, with traces of deuterium and lithium, and those traces still constrain cosmological models today. It did not produce heavy elements in abundance, and the reason is structural rather than merely thermal. The early universe expanded and cooled too quickly for complex nuclei to assemble and survive, and the density dropped before multi-step fusion could proceed. There are no stable nuclei with mass numbers 5 or 8, creating bottlenecks that halt the chain, like missing rungs on a ladder. In that first few minutes, the universe tried to build complexity, and the nucleus simply refused to cooperate. Those bottlenecks are not minor details, they shape the chemical universe, and they make the cosmos feel oddly contingent. Without stable mass 5 and mass 8 stepping stones, the early universe cannot climb smoothly toward carbon and beyond, no matter how many collisions occur. The cosmos begins with a simple inventory, then waits for stars to do the rest, as if chemistry itself must be postponed. The locked room of the nucleus becomes the gatekeeper of cosmic chemistry, deciding which atoms can exist in bulk. The central question shifts from what matter is made of to how matter becomes diverse, and why diversity required time. If just a few nuclear energy levels were shifted, would the universe have remained chemically barren? Stars provide the pressure and time that the early universe lacked, and they do it by turning gravity into a furnace. In stellar cores, gravity compresses plasma until fusion becomes possible, raising temperatures to millions of degrees and densities high enough for frequent collisions. Protons can overcome repulsion through quantum tunneling, forming deuterium and then helium, even when classical energy would be insufficient. The first steps are slow, because the weak interaction must convert protons into neutrons in the proton chain, and that slowness is why stars like the Sun live for billions of years. As stars evolve, they fuse heavier nuclei in stages, building carbon, oxygen, neon, and silicon, and each stage requires higher temperatures and shorter lifetimes. The visuals are a slow, tightening spiral, because each new fuel burns faster, as if the star is spending its remaining options. In massive stars, fusion proceeds toward iron, where binding energy per nucleon reaches a peak, and the curve stops offering easy rewards. The core becomes layered like an onion, with shells burning different fuels at different radii, and the visuals are almost architectural. Deep inside, silicon burning can assemble iron group elements in a chaotic equilibrium, while outer shells still fuse lighter nuclei. The star is not a calm sphere, it is a stratified engine with convection, neutrino cooling, and pressure battling gravity. Each layer is a temporary compromise, and the clock is always running. Even before collapse, the core is already a place where energy leaks away in neutrinos like heat escaping through invisible cracks. Iron is a turning point because fusion beyond iron costs energy rather than releasing it, and that reversal is decisive. A star can no longer support itself by fusing heavier elements in its core, because each reaction would drain pressure instead of replenishing it. When the core becomes iron-rich, pressure support fails, and collapse begins, accelerating in fractions of a second. The collapse triggers a supernova, and the supernova becomes both an ending and a factory, with shock waves, neutrino floods, and nuclear reactions igniting in a brief blaze. The heavy elements that planets need are forged in catastrophe, and the violence is part of the recipe. In the expanding debris, atoms that never existed in the early universe condense into dust, and that dust becomes the raw material of future worlds. Neutrons become central again in that factory, because they enable neutron capture, a pathway that bypasses the Coulomb barrier. Capturing a neutron does not require pushing like charges together, so it can proceed even when proton fusion stalls. In this process, neutron capture is slow compared to beta decay, and that pacing keeps nuclei near the valley of stability. A nucleus captures a neutron, then has time to beta decay if needed, stepping along the valley of stability, one careful move at a time. This occurs in aging stars, especially asymptotic giant branch stars, producing many elements up to bismuth, and the process is gradual, like careful assembly in a workshop. The star's outer layers can later drift away, carrying these nuclei into interstellar space as a quiet enrichment. In the R process, neutron capture is rapid compared to beta decay, and the tempo changes everything. Nuclei absorb neutrons so quickly, they are driven far from stability, building up neutron-rich isotopes that would never persist under ordinary conditions. After the neutron flood ends, beta decays cascade, converting neutrons to protons and building heavy neutron-rich elements, and the chain can leap across the periodic table. This requires extreme environments with enormous neutron flux, where matter is briefly soaked in neutrons like a storm. Modern evidence points strongly to neutron star mergers as major R-process sites, with some contribution from rare supernova conditions, and the evidence arrives in spectra and gravitational waves. When telescopes catch the fading glow of a kilonova, they are watching freshly made elements cooling into existence. These processes connect nuclear stability to the periodic table's shape, and they show that abundance is not simply about time or mass. Abundance peaks reflect nuclear shell closures, where certain neutron numbers are especially stable, and those closures act like waiting rooms along the capture path. The cosmos does not make elements uniformly. It follows nuclear structure, and the pattern is written into meteorites and starlight. Gold, platinum, and uranium are not just rare because they are heavy, and not just because they require extreme events. They are rare because the pathways to them require specific neutron conditions and specific timing, and because the locked room allows only certain exits. The periodic table is therefore not merely a list, it is a record of what the universe found easy and what it found difficult. The strong force remains the hidden protagonist in all of this, but it appears in two layers, and that layered nature matters. At the deepest level, quarks are bound by gluons through the fundamental strong interaction, a theory described by quantum chromodynamics. At the nuclear level, nucleons are bound by a residual strong force, a leftover of quark confinement that leaks beyond the proton's edge. The nucleus is like a molecule made from composite particles, held by an interaction that spills out of a deeper binding, and that spillover is powerful enough to build elements. The same force that confines quarks also, indirectly, allows chemistry to have more than one page. Residual strong force is accessible without being simplistic, and it offers an effective picture that still respects the underlying physics. Nucleons are color neutral overall, yet their internal color fields can polarize, and polarization can create attraction even between neutral objects. That polarization produces an effective attraction at short range, much like neutral atoms can attract through induced dipoles, though the mechanisms differ in detail. The analogy is limited, but it conveys an important point, and it keeps the story grounded. Nuclear binding is not a new fundamental force, it is an emergent remnant of a deeper one, and remnants can still reshape the universe. In the nucleus, what matters is not the full complexity of QCD, but the reliable outcome, short-range attraction with a hard core. Meson exchange provides a useful picture of that remnant, and it has a clear historical lineage. In this view, nucleons interact by exchanging mesons, especially pions, which carry the force between them, and the exchange can be visualized as a rapid handoff of momentum. The pion is not a mere mathematical trick, it is a real particle that can be produced and detected, and its existence confirms the intuition that forces can be mediated by particles. Exchange sets the range because heavier exchange particles imply shorter range forces, and the pion's mass points to a range of about a femtometer. The Yukawa idea links nuclear size to particle mass in a way experiments confirm, and it remains one of the cleanest bridges between theory and measurement. It is a rare moment in physics where a simple estimate points to a particle, and the particle is later found. This exchange picture also explains why nuclear forces saturate, which is one of the nucleus's most consequential quirks. Each nucleon interacts strongly only with neighbours within a short distance, so the binding does not grow without limit as nuclei get larger. Unlike gravity or electromagnetism, you cannot simply add more nucleons and get unlimited binding, because the force does not reach across the whole nucleus. Large nuclei become increasingly fragile, because repulsion grows with proton number, while strong binding does not scale the same way, and the balance tilts. This is why fission becomes possible for very heavy elements, and why the periodic table has a practical upper edge. It is also why nuclear sizes scale gently with mass number, growing like a crowded drop rather than expanding like a diffuse cloud. Fission and fusion are mirror stories of binding energy, and the mirror is the binding energy curve itself. Fusion releases energy for light nuclei as they move toward higher binding per nucleon, and the curve rewards them for becoming more tightly bound. Fission releases energy for very heavy nuclei as they split toward more tightly bound mid-mass fragments, and the curve rewards them for breaking apart. Both are consequences of the same binding curve, shaped by the strong force and Coulomb repulsion, and both can be quantified by mass differences. The nucleus stores energy not as fuel, but as configuration, and configuration can be rearranged. When we harness that rearrangement, we are exploiting a landscape of stability that nature already drew. The chapter's tension is that nuclear stability looks like a near miracle of competing rules, and the miracle is statistical rather than mystical. Electromagnetism tries to tear protons apart, and the strong force tries to hold nucleons together, but it can only act within a narrow reach. Quantum statistics and shell structure impose additional constraints, forcing nucleons into quantized arrangements with energetic costs. The weak interaction provides escape routes through decay, allowing the nucleus to change identity when the bookkeeping demands it. Stability is therefore not a default state. It is a negotiated outcome, and negotiations can fail. The locked room is not a fortress, it is a truce. To understand that negotiation, we need evidence, and evidence comes from scattering, because the nucleus cannot be opened like a box. Rutherford's experiment used alpha particles to reveal a compact nucleus, and the surprise was not merely that some particles bounced back. The surprise was that most passed through, implying emptiness, while a few deflected sharply, implying concentrated charge and mass. That pattern was the first clear sign of a locked room inside the atom, and it reshaped physics in a single decade. Modern nuclear physics uses beams of electrons, protons, and heavy ions to probe charge distributions and internal excitations, and the logic remains the same. Each experiment is a controlled collision, and each collision is a question asked in the only language the nucleus answers. The logic is the same as earlier chapters, where shorter wavelengths resolve smaller structure, because waves are rulers. Higher energy means finer spatial resolution, because momentum transfer sets the scale you can see, and the relation is quantitative. When an electron beam scatters, the angular pattern encodes the Fourier transform of the charge distribution, turning deflections into a kind of shadow image. Detectors do not see the nucleus directly, they infer it from probabilities, and the inference can be sharpened by better statistics. The locked room is reconstructed from what escapes, not from what is held. In a sense, the experiment builds a portrait from missing angles, and the portrait becomes clearer as the questions become sharper. Electron scattering maps nuclear charge radii and shapes with precision, revealing whether a nucleus is spherical, deformed, or vibrating in collective modes. Proton scattering and heavy ion collisions reveal nuclear potentials and collective excitations, including giant resonances that behave like coordinated breathing. Neutron scattering is harder because neutrons are neutral, yet it reveals complementary structure through strong interactions, and it can probe matter distributions rather than charge. Each probe couples differently, so each reveals a different aspect of the locked room, and none alone tells the whole story. The nucleus is reconstructed from deflections, not photographed directly, and that indirectness is part of its mystery. The more we learn, the more the nucleus looks like a living quantum object, not a rigid kernel. As energies rise, scattering stops treating nucleons as featureless, and the picture becomes more granular. At sufficiently high momentum transfer, experiments reveal that protons and neutrons have internal structure, and their apparent size emerges through form factors. Form factors deviate from point particle expectations, and deep inelastic scattering shows patterns inside, constituents that share the proton's momentum in shifting fractions. The nucleus begins to look less like a bag of billiard balls and more like a dynamic system of fields and constituents, where particles are excitations and interactions are constant. The strong forces story deepens rather than resolves, because every answer exposes a smaller question. Even the word inside becomes slippery, because the constituents are not little beads, but quantum entities defined by how they scatter. Particle accelerators become the necessary tool for that deeper story, because nature does not offer femtometer rulers on a tabletop. To probe smaller distances, you must deliver higher energies and measure rarer outcomes, and that means controlling beams with extraordinary precision. Accelerators provide controlled beams, high luminosity, and precise detectors that can reconstruct collision debris, turning chaos into data. The engineering is extreme because the questions are extreme, and the machines are built like instruments rather than weapons. The path from nuclear physics leads naturally toward facilities like CERN, where the strong interaction is studied at its fundamental level, and where the locked room is approached with ever harder knocks. In the tunnels, magnets guide particles with invisible hands, and the beams become the closest thing we have to a directed microscope of the subatomic. The nucleus also points toward astrophysical extremes, where its familiar form may fail and where the rules are tested under pressure. In a supernova collapse, electrons are forced into protons through inverse beta processes, producing neutrons and neutrinos, and the matter becomes neutron-rich in moments. Neutrinos carry away vast energy, and their interactions help drive the explosion's dynamics, even though they rarely interact with anything at all. The remnant can become a neutron star, where matter is compressed beyond ordinary nuclear density, and the scale flips again. The locked room becomes an entire object, a city-sized sphere with a mass greater than the Sun. Around it, space curves steeply, and light itself must climb out of a deep gravitational well. A neutron star is supported not by thermal pressure, but by degeneracy pressure and nuclear interactions, and the support is quantum mechanical in origin. Neutrons, as fermions, resist being squeezed into identical states, so compression forces them into higher momentum states that push back. That resistance is quantum mechanical, like electron degeneracy and white dwarfs, but at far higher density and with strong force corrections that cannot be ignored. Gravity presses inward with relentless force, and the star's stability depends on the equation of state of dense nuclear matter, a relationship between pressure and density. We do not fully know that equation, which makes neutron stars laboratories of ignorance, where uncertainty becomes measurable. When two neutron stars merge, the gravitational waves carry information about how easily that dense matter deforms, an echo of nuclear physics on a cosmic scale. At the boundary, nuclei may dissolve into more exotic phases, and the language becomes cautious because the data are incomplete. Neutrons and protons might rearrange into hyperons, meson condensates, or deconfined quark matter, depending on density and the details of the strong interaction. The strong interaction could shift from residual nuclear binding to a more direct quark-gluon regime, where confinement behaves differently under pressure. Observations of neutron star masses, radii, and gravitational wave signals constrain these possibilities, because different interiors produce different macroscopic signatures. The smallest things in the universe shape the largest catastrophes we can detect, and the chain of influence is unbroken. It is a humbling inversion, because our uncertainty about quarks becomes uncertainty about stars. The story returns to the neutron's dual identity, because the neutron is both a stabilizer and a transformer. In ordinary matter, neutrons hide inside nuclei, stabilizing and enabling diversity, and their presence allows heavy elements to exist at all. In radioactive nuclei, neutrons participate in transformations that change elements over time, and those transformations write clocks into bones and stones. In cosmic furnaces, neutrons enable the creation of heavy elements through capture and decay, and they do it without the Coulomb barrier's resistance. In neutron stars, neutrons dominate bulk matter, turning quantum rules into macroscopic structure and turning a particle into a landscape. The same neutrality that helps a nucleus hold together also helps the universe build complexity. This chapter also reframes what solid means at the deepest level, because solidity has layers. Earlier, solidity emerged from electromagnetic repulsion and quantum exclusion among electrons, the forces that keep your hand from passing through a table. Here, the nucleus is solid in a different sense, bound by a force that does not reach our fingertips and cannot be felt directly. The atom's center is not a hard bead, but a tight balance of interactions and probabilities, with motion and uncertainty always present. Matter's stability is an emergent illusion built from multiple layers of constraint, and each layer answers to different rules. When you press on a surface, you are feeling electrons, yet the mass beneath that feeling is almost entirely nuclear. The strong force, however, still refuses to be fully seen in the nucleus alone, because nuclear binding is only its shadow. Nuclear binding is residual, a shadow of a deeper confinement, and shadows can hint at shapes we cannot touch. Protons and neutrons behave like particles, yet scattering reveals they are composite, with internal distributions that shift with energy. Their internal constituents appear to be permanently trapped, never appearing as free fragments in detectors. The locked room has another locked room inside it, and the second lock seems even more absolute. It is one of physics' strangest facts that we can strike the proton, measure its parts, and still never collect those parts as separate objects. If protons and neutrons are themselves made of smaller parts, the next question becomes unavoidable. What are those parts, and what force keeps them confined so completely, even when we strike them with enormous energy? We can hit a proton hard enough to reveal its contents, yet we never pull those contents out as free objects, and and that is a profound clue. The descent continues because the strong force does not merely bind. It imprisons, and it turns the idea of inside into a deeper mystery. We leave the nucleus with a final tension that points forward, and the tension is the chapter's true doorway. The strong interaction explains why nuclei exist, yet it also hints that nucleons are not fundamental, and that the story has another layer below. The neutron stabilizes the nucleus, yet it can decay and rewrite identity through the weak force, turning stability into a temporary arrangement. The elements in our bodies were forged by these competing rules in stars and mergers, and their existence depends on narrow corridors of nuclear possibility. The smallest locked room in matter turns out to be a doorway into the next layer down, and the door is already ajar. We ended at the nucleus, where the strong force binds without showing its face. Now we open the next locked room, where protons and neutrons stop being fundamental. The camera moves from the soft blur of nuclear scales to a harsher, brighter world. Here, distance is measured in femtometers, and time is measured in flashes of interaction. The visuals tighten, numbers on a scale bar shrink, and the scene becomes a lattice of tracks, sparks, and abrupt turns. A proton is not a point-like bead with a fixed interior. High-energy scattering shows a shifting crowd of constituents carrying fractions of the proton's momentum. In the lab, those constituents behave like particles in detectors, leaving signatures that look crisp and countable. Yet they never appear as isolated trophies, even when we pour extraordinary energy into the attempt. The more violently we interrogate the proton, the more it answers with patterns rather than objects. This modern answer did not arrive all at once, and it did not arrive politely. It grew from decades of collisions, from bubble chambers to silicon trackers, and from arguments written in chalk. In the mid-20th century, the particle zoo looked like a catalogue without a grammar. Then scattering experiments, especially deep inelastic scattering, began to reveal regularities that felt like hidden gears. The deeper the probes went, the less the proton behaved like a solid object. It behaved like a dynamic system, where what counts as inside depends on how hard you look. Even the word constituent becomes conditional, defined by the resolution of the probe. The modern answer begins with a new inventory of matter. Quarks and leptons are the building blocks we can test as elementary today. Everything else is composite, including protons, neutrons, and the nuclei they assemble. That word elementary is not a philosophical claim, at least not yet. It is a statement about what has no detected substructure at the highest available resolution. It is a practical label, earned by experiments that keep failing to find seams. Start with the simplest hadrons, because they anchor the story. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. This is the valence picture, the minimal accounting that fixes the particle's identity. It is also the first hint that identity can be simpler than the underlying motion. In the visuals, we hold 3 points in a triangle, while the space between them seethes. Up and down are not directions, they are flavors, distinct quantum types. Their electric charges are fractional, with up at +2/3 and down at -1/3. Add the charges and the proton becomes +1, while the neutron sums to 0. The same arithmetic predicts the charges of many other hadrons with uncanny accuracy. It is simple enough to teach quickly, yet deep enough to be true. The surprise is that nature permits fractional charge, but only hides it inside color-neutral combinations. This arithmetic is clean, yet it hides the deeper surprise. Most of a proton's mass is not the quark's rest masses. The mass is largely energy stored in motion and fields, trapped by the strong interaction. In plain terms, the proton is heavy because it is busy. Quarks zip around relativistically, and gluon fields churn with stored energy that counts as mass. The proton's weight is a ledger of kinetic energy, binding energy, and quantum fluctuations. If you could freeze the proton and weigh only the bare quark masses, you would get a tiny fraction of the answer. Up and down quarks are light, only a few MeV each in the usual conventions. The proton is about 938 MeV, and the gap is the energy of QCD at work. It is one of nature's clearest demonstrations of E equals mc squared. Mass is not always stuff, because mass can be trapped dynamics. When you zoom in, the solid proton looks more like a storm confined by its own rules. Quarks combine into hadrons in 2 main families. Baryons contain 3 quarks, like protons and neutrons. Mesons contain a quark and an antiquark, and they often appear as short-lived exchange particles. In the visual language of the film, baryons feel like sturdy knots, while mesons feel like fleeting bridges. Both are real, both are measurable, and both are shaped by the same underlying rules. The Hadron spectrum becomes a kind of spectroscopy, energy levels of a strongly bound system. These combinations are not arbitrary, they obey a strict rule. Hadrons must be color neutral overall, even though their parts carry color charge. Color is not paint, it is the strong interactions version of charge. The name is a metaphor, chosen because we needed 3 labels and a way to speak. The physics is that quarks come in 3 charge types under the strong force. The metaphor helps the tongue, but the mathematics is what enforces the constraint. Color comes in 3 types, often labeled red, green, and blue. A baryon combines one of each to make a neutral whole. A meson combines a color with its matching anticolor, also producing neutrality. The neutrality requirement is not a preference, it is enforced by the structure of the theory. It is why the particles we see are always colorless, even though their interiors are not. In a clean animation, the colors cancel into white, then the cancellation refuses to be undone. The force carrier is the gluon, and it changes the rules compared to photons. Photons carry electric force but have no electric charge themselves. Gluons carry color charge, which means they interact with each other. That single fact makes the strong force qualitatively different from electromagnetism. It turns the field into a medium that can bind itself, twist itself, and store energy in its own structure. The strong force is not just a messenger, it is also a participant. That self-interaction is the engine of quantum chromodynamics, or QCD. QCD is a non-abelian gauge theory, meaning its symmetry operations do not commute. In plain language, the field has an internal geometry that is richer than a simple plus and minus. This richness is not decorative. It is responsible for confinement and for the running of the coupling. It is also why calculations become brutally difficult at low energies. The theory is compact on paper, yet it blooms into complexity in the real world. The strong field lines do not spread out and weaken like electric fields. They tend to bundle into tubes, storing energy as separation grows. If the film could show it, you would see a narrow filament between quarks, glowing brighter as it stretches. The energy is not diluted into space, it is concentrated, like a taut cable under tension. This is a visual metaphor for what the mathematics says about the field. The longer the tube, the more energy is packed into it, until something gives. Confinement is the chapter's central mystery, because it is absolute in ordinary conditions. Pull quarks apart and the energy in the field increases. At some point, the field creates a new quark, antiquark pair, and the system snaps into 2 color-neutral hadrons. The snap is not a mechanical break, it is particle creation from field energy. The universe refuses to leave color charge exposed. What looks like separation becomes multiplication. Nature pays the energy bill by making more matter, so we never see a single free quark in a detector. We see jets of hadrons, sprays of composite particles that carry the quark's original direction. In event displays, those jets look like narrow cones of tracks and energy deposits. They point back toward the collision, like arrows drawn by the debris. The quark's presence is inferred from patterns, not captured as an object. Even the jet's internal shape carries information, how the energy fragments, and how the shower broadens. This is not a failure of experimental skill, it is a property of the theory. QCD predicts that isolated color charge cost infinite energy in the limit of large separation. The strong force does not let you take a quark home. Even the language of pulling becomes misleading, because the field responds by reorganizing itself. Separation becomes creation, and creation becomes the only allowed escape. The detector records the compromise that the universe permits. Historically, this was a radical shift in what a particle could be. Earlier physics encouraged the idea that constituents could, in principle, be isolated and displayed. QCD suggests a different kind of fundamentality, where the constituents are real but not separable. It forces a new humility about what it means to have an elementary thing. Reality becomes something we access through consistent outcomes, not through possession. The quark is not a bead in a box. It is a rule-bound excitation inside a bound state. Yet QCD contains a second, almost paradoxical rule. At very short distances, quarks behave more freely. The interaction becomes weaker as energy increases, a feature called asymptotic freedom. If confinement is a trap at long distance, asymptotic freedom is a loosening at short distance. The same theory produces both behaviors depending on scale. It is one of the most elegant tensions in modern physics. The strong force is strongest where it binds, and gentler where we try to look closely. The coupling runs with scale, and the sign is opposite to electromagnetism. In QED, charges are screened and the effective coupling grows at short distances. In QCD, gluon self-interaction produces anti-screening, weakening the force at short range. You can picture a cloud of virtual gluons and quark pairs around a color charge. That cloud rearranges the field in a way that reduces the effective charge nearby. The vacuum is not passive. It reshapes the interaction depending on distance. This is why deep inelastic scattering works as a microscope. Hit a proton hard enough, and the probe sees quasi-free partons for an instant. Then confinement reasserts itself, and the outgoing energy hadronizes into jets. The instant is short, but it is long enough for the interaction to register in the detector. The proton reveals its internal bookkeeping through how it breaks. In a graph, the scattering angles and energies become a coded message, decoded into structure functions. The Parton model was once a daring simplification, and it became a map. In scattering data, structure functions encode how momentum is shared among constituents. As the energy scale changes, those distributions evolve in predictable ways. Gluons become increasingly important at high energies, carrying a growing share of the proton's momentum. The proton, at high resolution, looks less like three quarks and more like a crowded sea. The sea is not decorative noise. It is a measurable component that reshapes cross-sections. The documentary's central question sharpens here. What is everything made of if the deepest pieces cannot be isolated? We are forced to define reality by interactions and outcomes, not by possession. The detector does not hand us a quark, it hands us a statistical fingerprint. We learn to trust the fingerprint because it repeats with mathematical reliability. And we learn to doubt our instincts because the fingerprint is consistent even when the picture feels strange. To make QCD accessible, keep the picture minimal but honest. Quarks carry color charge and exchange gluons. Gluons carry color too, so the field can bind itself into a confining structure. In a visual sequence, imagine lines of force that do not fade into the distance. They tighten, they braid, and they resist being stretched. The strong force is not just strong, it is architected. Its architecture is why protons exist at all, and why they refuse to be dismantled. At nuclear distances, we feel only a residual strong force. It is the leftover of color fields leaking from color-neutral nucleons. Inside a proton, we face the fundamental strong force directly, and it behaves differently. The residual force is like a faint stickiness between neutral objects, similar in spirit to molecular forces. The fundamental force is the underlying glue, and it does not politely turn off. The nucleus is held by a shadow of QCD, but the proton is built by QCD itself. This difference explains why the nucleus was a shadow, not the source. Nuclear binding is powerful but limited in range. Confinement is deeper and more rigid, and it shapes what counts as a particle. In the nucleus, protons and neutrons keep their identities most of the time. Inside them, identity is maintained by constant exchange, constant fluctuation, and constant rearrangement. Stability is not stillness, it is balance. The camera lingers on that paradox. Permanence made from ceaseless motion, now widened from QCD to the full standard model map. It is not a theory of everything, but it is our best tested catalogue of fundamental interactions. It organizes matter fields and force fields into a single quantum framework. The map is drawn with symmetries, and the symmetries dictate what interactions are allowed. When the symmetries are exact, conservation laws follow like shadows. When symmetries are hidden, masses and mixings appear, quietly rewriting what can happen. Matter comes in two families of fermions. Quarks feel the strong force, electromagnetism, and the weak force. Leptons do not feel the strong force, but they do feel electromagnetism if charged, and all feel the weak force. Fermions have half-integer spin, and they obey the Pauli exclusion principle. That single rule is why electrons build chemistry instead of collapsing into one state. It is also why matter has rigidity, why solids resist compression, and why atoms have layered structure. There are three generations repeating the same pattern with heavier masses. The first generation builds ordinary matter with up and down quarks, the electron and the electron neutrino. The heavier generations appear in cosmic rays and accelerators, then decay quickly. Their brief lives are not pointless, because their existence shapes precision tests and rare processes. They also hint at a pattern we do not yet understand. Why should nature repeat itself twice more, like an echo that fades yet refuses to vanish? Force carriers are bosons, each tied to a symmetry. The photon carries electromagnetism and couples to electric charge. The gluon carries the strong interaction and couples to color charge. These are gauge bosons, meaning they arise from requiring local symmetry in the theory. In plain language, the equations insist on a messenger field to keep the rules consistent everywhere. The force is the price of demanding that the laws look the same at every point in space and time. The W and Z bosons carry the weak interaction. They are massive, which makes the weak force short range. Their exchanges change particle types, enabling beta decay and the flavor changes that reshape nuclei. In beta decay, a down quark can transform into an up quark, and a neutron can become a proton. That transformation is not a metaphor, it is a measured process with a calculable rate. The weak force is how the standard model allows identity to change. In the visuals, a track abruptly ends, and a new set of tracks begins, linked by an invisible exchange. This is where the word elementary needs careful handling. In the standard model, quarks and leptons are treated as point-like, with no measured size. The force carriers are also point-like excitations of fields. Point-like does not mean simple, because even point-like fields can have complex quantum behavior. It means that, so far, scattering experiments have not revealed internal structure. The point is not that we have seen infinity, but that we have not yet seen an edge. But elementary can mean two different things. It can mean truly fundamental, with no deeper layer. Or it can mean unresolved by current experiments, a limit set by energy, statistics, and detector reach. Physics has learned to respect that distinction, because history has punished overconfidence. Atoms were once thought indivisible, and nuclei were once thought fundamental. Each time, better microscopes change the story, so we keep the word, but we keep a question mark beside it. Quietly, persistently. Accelerators become the narrative engine because they turn energy into resolution. Higher momentum transfer corresponds to shorter wavelengths and smaller distances. Bigger machines do not just smash harder, they see finer. The beam energy sets the scale of what can be produced, but the momentum transfer sets the sharpness of the probe. In modern collider language, energy is both a hammer and a lens. The ring is a microscope whose objective is made of magnets and timing systems. There is also a deeper reason accelerators matter, and it is almost philosophical. They let us recreate conditions that do not exist naturally on Earth today. For a moment, in a controlled place, we can approach the temperatures and densities of the early universe. That does not make the collider a time machine, but it makes it a laboratory for primordial rules. We test the same interactions that once shaped cosmic history. In the glow of a control room, human hands adjust parameters that momentarily mimic the first instance after the Big Bang. CERN is the emblem of this method, a modern version of Rutherford's question. Beams are prepared, focused, and collided with extreme control. Detectors then reconstruct the invisible from the debris that survives. The ring itself is a monument to precision engineering, where magnets guide protons like rails guide trains. Radio frequency cavities push the beams, turn by turn, until their energies become immense. The collisions are planned, but the outcomes remain quantum. On screen, a clean, silent tunnel holds a storm of circulating particles, unseen, yet precisely shepherded. A collider event is not a photograph, it is a forensic reconstruction. Charged particles leave tracks in magnetic fields, curving by momentum and charge. Calorimeters measure deposited energy, while timing layers separate overlapping collisions. Each subsystem is a different sense organ, and the full detector is a synthetic organism. The event display is a translation, turning electronic pulses into geometry and color. What we see is a carefully calibrated inference. Behind every line is a chain of corrections, alignment, noise subtraction, and pattern recognition. Most crucial products are not seen directly. Neutrinos escape, leaving missing transverse momentum. Short-lived particles decay instantly, leaving displaced vertices and characteristic combinations of tracks. A heavy flavor hadron might travel a fraction of a millimeter before it decays, and that tiny offset becomes a clue. A tau lepton may leave only a brief trace, reconstructed from its decay products. The invisible becomes visible through imbalance and geometry. The detector learns to notice what is not there, an absence that points to a real particle. Even the particles we do see are not seen in isolation. They pass through layers of material, they radiate, they scatter, and they sometimes masquerade as one another. Reconstruction algorithms compare hypotheses, fitting tracks to expected patterns. The detector must be aligned, calibrated, and understood in detail, because tiny biases can mimic signals. In the end, the story is told by distributions, not by single dramatic frames. The drama is statistical, built from millions of ordinary events that reveal a rare shape. The key observable is probability, not certainty, echoing earlier chapters. Cross-sections quantify how often a process occurs at a given energy. Luminosity determines how many collisions are needed to catch rare events. A large cross-section is a common process like ordinary jet production. A tiny cross-section is a whisper, like Higgs production or rare decays. The experiment is a negotiation between rarity and patience. Every plotted point is a compromise between what nature offers and what the machine can deliver. This is why discovery requires scale, and why it also requires restraint. New particles are often produced in tiny fractions of collisions. You need enormous datasets to separate a signal peak from a background continuum. Backgrounds are not mistakes. They are real physics that happens more often. The art is to model them, measure them, and then ask whether an excess remains. The question becomes, is the bump a new particle, or a misread shadow cast by known processes? The standard model's power is that it predicts those rates with precision. Quantum field theory provides the calculation language, with amplitudes that interfere. The same probabilistic structure that shaped photons and electrons now governs quarks and gluons. Interference can enhance a process or suppress it, depending on phase and symmetry. In the data, those quantum subtleties appear as shifts in distributions and branching ratios. The equations are abstract, but their fingerprints are concrete. A tiny deviation can be a tremor from something heavy and unseen. Yet the standard model has a famous missing piece if you remove one field. Without the Higgs mechanism, the equations cannot give W and Z bosons their observed masses, while preserving gauge symmetry. The weak force would look nothing like what we measure. The theory would predict long-range weak forces, and it would fail spectacularly. The Higgs mechanism is not an optional patch. It is the structural support. It is the difference between a consistent rulebook and a broken one. The Higgs field is a cosmic background, present even in empty space. Particles acquire mass through interaction with that field, not through being made of more stuff. Mass becomes a measure of coupling, not a measure of hidden material. Some particles couple strongly and become heavy, while others couple weakly and remain light. The photon does not couple in the same way, and it stays massless. This is a rulebook property, not a material ingredient. In a visual metaphor, space itself has a texture, subtle, everywhere, and impossible to scrape away. The Higgs boson is the field's quantum excitation, the detectable ripple. It is unstable and decays into other particles quickly. Its existence is inferred from excess events in specific decay channels. In visuals, the Higgs itself never appears as a track, only as a bump in a reconstructed mass spectrum. The bump is subtle, sitting on top of backgrounds that must be understood with care. Discovery is not a single event, it is a statistical emergence. The camera can linger on the histogram, bars rising and falling, until one region refuses to be explained away. CERN's Large Hadron Collider confirmed a Higgs-like particle in 2012. 2 experiments saw consistent signals in gamma pairs and 4-lepton final states. The measured properties match the standard model Higgs within current uncertainties. That agreement was not automatic because many alternative models predicted different rates and decay patterns. The early measurements were a beginning, not a final portrait. Each new dataset sharpens the question of whether the Higgs is exactly as expected. The story continues in decimals, small shifts in couplings that could reveal a deeper structure. This confirmation was a climax, but it was not closure. The Higgs does not explain why couplings take their values. It does not explain why there are 3 generations, or why neutrinos have such tiny masses. It also does not explain why the Higgs mass itself is what it is, rather than vastly larger. The standard model can describe, but it does not always illuminate. The map is accurate, yet some labels feel arbitrary. We can measure the numbers to many significant figures, but we still do not know why those numbers exist. It also does not explain why the universe contains more matter than antimatter. The standard model allows some CP violation, but not enough to account for the observed asymmetry. Our existence still looks like an unsolved imbalance. In the early universe, matter and antimatter should have annihilated almost completely. Something tipped the scales, leaving a residue of matter that became stars and planets. The question is not academic because it is literally the reason anything remains. When we look at the night sky, we are looking at the outcome of that ancient bias. Neutrinos deepen the mystery because they break the simplest standard model picture. Oscillation experiments show neutrinos change flavor, which implies they have mass. The minimal standard model predicts massless neutrinos, so something must be added. The oscillations are a quantum interference effect across distance and time. A neutrino is produced in one flavor state, but it propagates as a mixture of mass states. By the time it arrives, its identity can be different. The film can show 3 waves sliding out of phase, then recombining into a new flavor. That fact forces us to revise the story of elementary again. Neutrino masses are tiny, but they are not zero. Their smallness suggests either extremely weak couplings or a mechanism that hides mass behind a high scale. The standard model can be extended to accommodate them, but the extension is a signpost. It tells us the current map is not the whole coastline. The neutrino becomes a messenger from beyond the neatest version of our theory. Dark matter is another pressure point, because it is gravitationally obvious and particle physically silent. Galaxies and clusters require extra mass that does not emit or absorb light. The standard model has no suitable stable, neutral, abundant particle to fill that role. In visuals, you would see starlight tracing spiral arms, while gravitational lensing traces a heavier invisible scaffold. The universe behaves as if a shadow substance outweighs the luminous one. We can measure its pull, but we do not know its identity. The question hangs in the air. What kind of particle can be everywhere and still refuse to speak to our detectors? Dark energy is even stranger because it accelerates cosmic expansion. It behaves like a property of space itself, yet its measured value is tiny compared to naive quantum vacuum estimates. The mismatch is one of the largest in physics. In the film, the expansion is not a blast, but a quiet stretching of the cosmic grid. The farther galaxies are, the faster they recede, as if space is gaining a persistent outward pressure. The equations can include it, but the meaning remains elusive. We can name it, we can plot it, yet we cannot explain why it is so small and not zero. Gravity remains absent from the standard model's quantum structure. General relativity describes spacetime curvature with extraordinary success, but we do not have a complete tested quantum theory that unifies gravity with the other forces. In daily life, gravity dominates our intuition. Yet in particle interactions, it is astonishingly weak. The mismatch in strength is part of the puzzle. The deepest description of matter still does not fully include the stage it plays on. The more precisely we describe the actors, the more we notice the missing script for the theatre. So the standard model is both triumphant and incomplete. It predicts collider data, atomic precision tests, and particle decays across many orders of magnitude. Yet it leaves key parameters as inputs, and it leaves major cosmic components unexplained. It is like a machine with dials that must be set by hand. The machine then runs flawlessly, but it does not tell you why the dials have those values. That tension is the engine of modern curiosity. We're grateful for the map, and uneasy about its blank margins. Return to Confinement, because it is the chapter's emotional core. We can probe quarks as if they are real constituents. We can measure their distributions, spins, and contributions to proton structure. We can map pattern distribution functions and watch them evolve with scale. We can compare data from different experiments and see the same internal logic. The proton becomes a studied landscape even if it is never directly opened. We learn its geography by how it responds to impact, like mapping a cave by echoes. But we cannot isolate them, and that constraint reshapes what we mean by matter. The deepest pieces we can touch are not free objects. They are confined excitations whose individuality is limited by the rules that define them. It is a strange kind of reality, where the constituents are undeniable but inseparable. The world is not built from marbles, It is built from relationships enforced by symmetry. The question becomes sharper. If you cannot separate a thing, in what sense do you claim it exists? Even the proton's interior is not static. Gluons carry much of the momentum at high energies. Quark, antiquark pairs flicker into existence as part of the field's dynamics, and the proton becomes a C, not a trio. The valence quarks set the proton's quantum numbers, but the C shapes much of its behavior. In a vivid visual, the interior is a storm, eddies of field energy, brief pair creations, and constant exchange. The proton is stable, yet its stability is a constant motion. The calm exterior is a statistical illusion, created by countless microscopic rearrangements. This is where the documentary's conclusion theme comes into focus. The smallest things are not tiny beads, they are patterns in fields. Particles are events and excitations defined by symmetries and interactions. A particle is what the detector counts, but the field is what the theory insists exists everywhere. The count is discrete, yet the underlying object is continuous. That duality is not a contradiction, it is the quantum structure. We live in a world where the click is real, and the wave beneath it is real too. Quantum field theory ties the story together with a single stance. Fields are fundamental objects spread through space. Particles are quantized disturbances of those fields, counted in detectors as discrete outcomes. The vacuum is not empty, because fields still fluctuate within quantum limits. Those fluctuations are constrained, and they can have measurable effects. In this sense, nothing is an active medium with rules. The emptier space still has a character, defined by what it permits and what it forbids. Yet we still ask whether quarks are truly point-like. Experiments place upper limits on any size, pushing it smaller with higher energies. But a limit is not a proof, and the question remains open. If quarks had substructure, scattering at sufficiently high momentum transfer could reveal deviations. Those deviations might appear as contact interactions or altered angular distributions. So far, the data remains stubbornly consistent with point-like behavior. The silence is informative, but it is not the same as certainty. Some proposals suggest deeper layers, like compositeness, extra dimensions, or new symmetries. Others suggest that the standard model is effective, a low-energy approximation of a deeper theory. Each idea predicts subtle deviations and accelerators search for them. The search is not only for new particles, but for small mismatches in precision observables. A tiny anomaly can be a doorway, if it survives scrutiny. The most valuable signal might be the one that looks boring at first, until it refuses to go away. So far, the standard model keeps winning, and that victory is itself unsettling. It means new physics may hide at higher energies, or in rarer processes, or in precision anomalies. The absence of clear cracks becomes part of the mystery. It forces us to ask whether nature is simply economical, or whether our tools are still too blunt. When the map fits too well, we start wondering what it is not showing. Are we looking in the wrong place, or is the universe more subtle than our expectations? CERN's future machines are planned around this tension. Higher energies would extend the reach for new particles. Higher precision would test the Higgs and top quark as portals to hidden sectors. Precision is not a consolation prize, because it can expose heavy physics indirectly. A heavy new particle can alter loops and shift rates even if it cannot be produced directly. In that way, the unseen can still tug on the scene. The next discoveries may arrive as a fractional percent, small enough to miss, large enough to matter. But there is a deeper philosophical edge that physics cannot avoid. If the fundamental description is fields and symmetries, then particles are not the base layer. The base layer is the rulebook that governs what can appear. Symmetry is not merely aesthetic, it is a constraint that shapes reality. When symmetry breaks, new phenomena emerge, and the world acquires structure. The universe looks the way it does because certain symmetries are exact and others are hidden. The laws are not just descriptions, they are boundaries that sculpt what exists. This returns us to the central question in its sharpest form. What is everything made of beneath atoms and beneath nucleons if the answer is not a substance? The answer may be a set of quantum fields and constraints that permit certain excitations. That is a strange answer for human intuition, because it replaces material with mathematics. Yet it is an answer that keeps passing experimental tests. The deeper we go, the more matter looks like a consistent set of permissions. Transition to the final chapter with the unresolved horizon. If quarks are point-like and confinement prevents direct isolation, then our deepest access is indirect and statistical. We have reached the deepest pieces we can touch, but we have not proven they are the bottom. The locked room opens, and behind it is another corridor. Each door reveals a deeper rule, and each rule raises a new question. The camera pulls back, past the proton, past the detector, past the ring, until the unanswered space becomes the subject. The standard model is a map of what we can currently name. It may be the final layer, or it may be the shoreline of a deeper ocean. The next step is to ask what lies beyond the map, and how we would know. If the universe has hidden sectors or deeper symmetries, they may announce themselves only through faint distortions in what we already measure. And if they never announce themselves, we must ask what kind of knowledge physics can ultimately claim. Everything we touched in this film felt solid, yet it was mostly empty space, a lattice of forces holding distance in place. The closer we looked, the more solidity dissolved into patterns, clouds of probability, pulses of energy, and rules that never show themselves directly. We kept dividing matter down through atoms, electrons, photons, nuclei, and quarks. Now the descent reaches a strange boundary, where smallest stops meaning a smaller object, and starts meaning a smaller question. Our instruments do not shrink like imagination does, because lenses and detectors are made of the same matter we're trying to interrogate. To resolve smaller distances, we must use shorter wavelengths and higher momentum transfer, which is the same demand written in different languages. Higher momentum means higher energy, and higher energy means rarer events and harder backgrounds, more noise, more radiation, more confusion to subtract. The microscope becomes a collider, and the price of sharpness is violence, because the probe must strike hard enough to reveal structure. In the visuals, the gentle beam of a classroom diagram becomes a storm of tracks, sparks, and curved trajectories inside a detector. This is the measurement frontier that has driven every step of the story, and it has a history carved into steel and concrete. Rutherford needed alpha particles to see the nucleus inside the atom, and his famous gold foil experiment turned plum pudding into a planetary picture. Deep inelastic scattering needed far higher energies to see quark structure inside nucleons, and the messy spray of hadrons became a readable signature. Each new layer demanded a new machine, because nature hides small scales behind energy thresholds and behind the quantum limits of resolution. Even the language of seeing is metaphorical. What we really do is infer structure from scattering angles, cross-sections, and statistical patterns. But there is a limit that is not merely practical. Push energy high enough, and gravity, usually negligible in particle physics, stops being ignorable because energy itself gravitates. At extreme energies, concentrating energy into a tiny region curves space-time strongly, and curvature is not a side effect. The act of probing can distort the stage you're trying to measure, as if the ruler bends the floor while it is being laid down. In a visual montage, the clean grid of space-time lines begins to warp around a bright point of energy. The Planck length is the scale where this collision of ideas becomes unavoidable, not because we have reached it, but because our equations begin to argue. It is about 10 to the minus 35 meters, unimaginably smaller than a proton, smaller by a factor that defeats ordinary intuition. It is built from Planck's constant, the speed of light, and Newton's gravitational constant, a dimensional combination that feels like a warning label. It is not a measured wall, but a sign that our current theories stop agreeing about what distance even means. At around the Planck scale, quantum mechanics demands fluctuations and uncertainty in energy and position, and it permits virtual processes that briefly borrow energy from the vacuum. General relativity demands that energy density curves space-time, possibly forming horizons, and horizons are one-way boundaries for information. Put those together, and distance becomes unstable as a concept, because attempts to localize an event may create the very gravitational trap that hides it. The ruler becomes part of the system, and the system may answer by hiding information behind a tiny black hole's horizon. We are forced to ask a thought-provoking question. If measurement creates an event, what happens when the event reshapes the arena of measurement? This is where we return to quantum field theory, because it already changed what a particle means in the first place. In QFT, fields are the basic objects spread throughout space, and they carry charges that dictate how they can interact. Particles are quantized excitations, counted as discrete detector clicks, and those clicks are the only objects we ever truly record. The electron is not a tiny sphere, it is an excitation of the electron field, with properties fixed by symmetry and by the way it couples to other fields. The vacuum in this view is not empty, even when every detector is quiet and every classical source is removed. It is the lowest energy state of all fields, still alive with fluctuations, because the uncertainty principle forbids perfect stillness. Those fluctuations are constrained by uncertainty and by the symmetries of the theory, and they can be calculated with extraordinary accuracy. They leave measurable traces like the Lamb shift and the Casimir force, where nothing pushes on metal plates with a real, quantifiable pressure. In the visuals, darkness is never truly black. Subtle ripples and transient pairs flicker at the edge of perception. So the question, what is everything made of, becomes less about substance and more about structure, because the word made assumes a kind of material stacking. It becomes about which fields exist and how they interact, including the gauge fields that mediate forces. Matter is a stable pattern in a set of rules, not a pile of miniature beads, and stability itself is a triumph of quantum statistics. The deeper we went, the more thing became relationship, and the more the universe resembled a grammar rather than a warehouse. Yet QFT also sharpens the puzzle, because it treats space-time as a smooth background, a stage that does not participate in the quantum drama. Fields live on that background, and their excitations move through it, exchanging quanta and conserving charges. Gravity, in general relativity, is not a force on space-time. Gravity is space-time geometry itself, and geometry is what tells every particle how to move. So the final locked room is not inside the proton. It is the interface between quantum fields and space-time, where our two best languages describe reality with incompatible assumptions. We can quantize the fields with stunning precision, and we can curve space-time with stunning precision, and both descriptions have passed brutal experimental tests. We cannot yet do both in one tested framework, especially when energy densities become so high that quantum fluctuations of geometry should matter. One candidate idea is string theory, framed carefully as a proposal, not a confirmed layer. It replaces point particles with tiny vibrating strings, which means interactions can be spread out rather than concentrated at a single mathematical point. Different vibration modes appear as different particles, including ones that resemble known quarks and leptons, and the spectrum is shaped by consistency conditions. The hope is that one object, a string, could unify the inventory, turning the particle zoo into a single underlying mechanism. String theory also naturally includes a quantum version of gravity, which is one reason it has remained compelling for decades. A particular vibration mode behaves like a graviton, the hypothetical quantum of gravitational waves, and that emergence is not inserted by hand. That is a major attraction, because it offers a route to a consistent quantum gravity, at least in principle. It suggests that gravity is not an add-on, but part of the same quantum language, another note in the same vibrating instrument. But strings come with costs that are not cosmetic, and they change what space might be. The mathematics typically requires extra spatial dimensions beyond the three we experience, because the theory's internal consistency demands them. Those dimensions must be hidden or compactified in specific ways, curled up so tightly that ordinary motion never enters them. The landscape of possible compactifications becomes enormous, and prediction becomes difficult, because many different hidden shapes can reproduce the same low-energy physics. String theory has produced deep mathematical tools and surprising connections between theories, including dualities that reveal the same physics in radically different descriptions. It has also struggled to produce unique, testable predictions at accessible energies, which is the standard that turns a framework into a settled theory. The Planck scale is far beyond our colliders, and indirect signatures are subtle, often entangled with astrophysical uncertainties. So string theory remains a powerful framework, but not an experimentally settled answer, and its status must be stated with discipline. Another path is loop quantum gravity, which starts from general relativity and tries to quantize geometry itself. In this approach, areas and volumes come in discrete units, and the continuum becomes an approximation that emerges at large scales. Space-time becomes a network of quantum relations, not a smooth continuum, and geometry is built from links and nodes rather than coordinates. The smallest becomes a smallest chunk of geometry, a pixel size for space itself, though time and dynamics remain subtle. Loop quantum gravity is more conservative about dimensions and about known physics, because it does not require extra spatial directions. It aims first to make quantum spacetime consistent, then to recover classical spacetime at large scales, the way thermodynamics emerges from atoms. It has candidate results for black hole entropy, and for resolving singularities, replacing infinities with quantum structure. It still faces open questions about unifying with the standard model and about clear experimental tests. Because quantum geometry is hard to make speak in detect accounts, these approaches share a theme that matters for our central question, and it is a theme that quietly rewrites the meaning of made of. The smallest things may not be particles at all, because particles may be excitations that require a space-time stage. The smallest things may be the quantization of space-time, or the rules that permit fields to exist, or the symmetries that constrain every interaction. The foundation might be structure, not stuff, and that possibility is both elegant and unsettling. Return to what we can actually measure, because cosmology offers a different kind of accelerator, one built by nature and run only once. The early universe reached energies far beyond any human machine, and its conditions were not engineered but inevitable. In its first fractions of a second, temperatures and densities were extreme, and the plasma of fields was closer to the symmetries of the high-energy laws. If new physics exists, the early universe may have used it, and the evidence may be written into patterns we can still observe. Inflation is a central example, still compelling and still questioned, because it sits at the edge between explanatory power and unknown mechanism. It proposes a brief era of accelerated expansion that smoothed the universe in seed structure, ironing out curvature and diluting relics. Quantum fluctuations during inflation could be stretched to cosmic scales, turning microscopic uncertainty into macroscopic pattern. Those fluctuations could become the initial pattern for galaxies and the CMB, like a faint fingerprint pressed into the oldest light. If inflation happened, it may carry fingerprints of physics beyond the standard model, and those fingerprints would be subtle but profound. Primordial gravitational waves could imprint B-mode polarization in the CMB, a twisting pattern that would be hard to mimic by later processes. Deviations from perfect Gaussian statistics could hint at new fields, or at interactions during inflation that left non-random correlations. Even the absence of signals constrains which high-energy stories remain plausible, because silence can rule out whole classes of models. Other primordial relics could also speak, and each one is a different kind of measurement made across billions of years. The abundance of light elements tests early universe nuclear reactions, and it checks our understanding of expansion and particle content. The distribution of matter tests dark matter properties and interactions, because clustering depends on how matter moves and cools. The expansion history tests dark energy, and the vacuum's effective energy density, forcing us to confront the strange fact that empty space behaves like a source of gravity. Cosmology becomes a laboratory where the universe ran the experiment once, and we reconstruct it from the data it left behind. But the human limit is not only technological, and it is not only the size of our machines. Quantum theory includes uncertainty as a built-in feature of reality, not a flaw of instruments, and it sets a hard boundary on what can be simultaneously sharp. Measurement is an interaction that entangles system and detector, and it selects definite outcomes from a spread of amplitudes, which is why outcomes look classical after the fact. We can calculate probabilities with precision, yet the why this outcome question remains philosophically sharp, because the mathematics does not hand us a single narrative. There is also incompleteness in a more ordinary sense, and it shows up as a list of numbers we must accept from experiment. Our theories contain parameters we measure but do not derive, like particle masses and mixing angles, and even the strengths of forces run with energy. The standard model works, yet it does not explain its own inputs, and it leaves puzzles like the hierarchy of scales sitting in plain view. Mathematics can describe patterns perfectly, while intuition lags behind, and the gap between them is where mystery lives. So what counts as an explanation when the picture stops being visualizable, and when the best description is a set of equations? Sometimes explanation means compressing many facts into a small set of rules, the way Maxwell compressed electricity and magnetism into one framework. Sometimes it means finding a deeper symmetry that forces the numbers, turning arbitrary constants into consequences. Sometimes it means admitting that a question may be ill-posed, because it assumes a classical kind of thing where only a quantum relation exists. Now we answer the central question as honestly as the evidence allows. The best current answer is that everything is made of quantum fields and their excitations, and that made means described by, at the deepest tested level. Atoms, electrons, photons, neutrons, and quarks are stable excitations and bound states, governed by gauge symmetries and quantum statistics, and verified in countless experiments. The vacuum is structured, and empty space has measurable properties, which means absence is not the same as nothing. The honest boundary is quantum gravity, and whatever lies at the Planck scale, where our tested theories stop fitting together cleanly. We do not know whether strings, loops, or something else is the correct next layer, and we should resist pretending that elegance is evidence. We do not know whether spacetime is fundamental or emergent, like temperature emerging from molecular motion. We do not know whether there is a final smallest or only new descriptions, each one deeper and stranger than the last. This is not defeat, it is the edge of knowing, and edges are where science is most alive. The frontier is defined by what we can test, and by what consistent mathematics can hold together without contradiction. The smallest things in the universe may be beyond direct reach, yet they may still leave indirect traces in precision measurements and cosmic relics. The question becomes a quiet challenge. What signature would convince us that spacetime itself has atoms? We began with solidity, and we end by reinterpreting it, because the everyday world is a successful illusion built from stable rules. The table is not a continuous block, but a choreography of electron fields and photon exchange, with electromagnetic repulsion doing most of the holding up. The mass in your hand is mostly QCD energy bound inside nucleons, energy stored in fields and motion rather than in tiny solid cores. The stability of nuclei depends on quantum rules that forbid collapse and permit only certain arrangements, and those rules are as real as the wood grain you can see. And beneath that visible crust, there is an ocean of quantum rules, deeper than any picture we can draw. Fields fluctuate even in vacuum, symmetries constrain what can exist, and interactions decide what can persist, sometimes for an instant, and sometimes for billions of years. The everyday world is a thin, reliable surface over deep uncertainty, and reliability itself is a statistical miracle repeated without fail. When we ask for the smallest things, we are really asking for the deepest rulebook, and for the origin of the rules. The final image is not a particle, but a perspective shift, like stepping back until the familiar becomes abstract. Atoms, electrons, photons, neutrons, and quarks are not the end of matter. They are the part of the universe that our questions can currently touch through detectors, telescopes, and the mathematics that translates clicks into meaning. Beyond them, the universe may be made less of things, and more of relationships we are still learning to read, one careful measurement at a time. We began with a simple touch, a hand on a door, and discovered that solid is a negotiated truce between quantum rules. Atoms are mostly emptiness, electrons are not tiny planets, but standing wave probabilities, and the stiffness of matter rises from electromagnetic exchange and Pauli's refusal to share. We followed the messenger, photons, and learned that light is both wave and particle, a carrier of forces and a record of cosmic history, from spectral barcodes to the afterglow of the microwave background. Then we pushed into the nucleus, where neutrons and binding energy revealed the strong force's short, fierce logic, and the weak force quietly rewrote elements through radioactive clocks. Beneath protons and neutrons we met quarks and gluons, trapped by confinement yet exposed through jets and scattering, where most mass is not stuff at all, but energy held in fields. And at the edge of our descent, the Planck scale reminded us that sharper questions require harsher probes, until gravity itself may censor the smallest distances, turning measurement into a boundary. Across every chapter, the pattern repeated, reality became less like a pile of bricks, and more like a choreography of interactions, symmetries, and probabilities, inferred from faint traces rather than directly held. What looked like a straightforward inventory, atom, electron, photon, neutron, quark, became a story about how knowledge is made, because every experiment is also an intervention. The double slit did not merely surprise us, it warned us that what happened and what can be known are sometimes the same question, separated only by information. Even the vacuum refused to stay empty, whispering through the Lamb shift and the Casimir force that nothing has structure when fields are fundamental. And yet, for all this precision, the standard model still leaves blank margins, neutrino masses that should not be there, a universe made of matter instead of antimatter, and a cosmos dominated by dark matter and dark energy we cannot yet name. We ended, not with a final particle, but with a horizon, where quantum fields meet curved spacetime, and our best ideas, strings, loops, or something stranger, compete to explain what space-time itself is. In that sense, the smallest things in the universe are not beads at the bottom of a box. They are the rules that let patterns persist. The deeper we looked, the more the objects dissolved into relationships, and the more the universe resembled a grammar, spoken by symmetries and enforced by conservation laws. Matter became an emergent surface, a stable illusion produced by quantization, exclusion, and the ceaseless exchange of force carriers. And the cosmos, from the first seconds after the Big Bang to the chemistry in our blood, turned out to be the same story told at different scales, a single set of laws writing itself into stars, stones, and skin. In the cold open, we asked, when we peel reality back past atoms, past electrons and photons, and reach quarks and fields, are we finding the final building blocks, or the edge of what can ever be known? The answer so far is both, because what we find is not a last object but a deeper description, where particle is a convenient word for a quantized ripple in a field. And the edge is real, not as a wall of ignorance but as a principle, that to ask smaller questions we must spend more energy, until space-time itself may answer by changing the rules. So what is everything made of beneath atoms and beneath subatomic particles? It is made of excitations in quantum fields, stitched together by interactions and constrained by symmetries that feel like laws, because they are the universe's most reliable habits. Yet those habits are not complete, because gravity still stands apart, dark matter still hides its identity, and the constants we measure still refuse to explain themselves. Our question becomes sharper now, not what is the tiniest thing, but what is the simplest set of rules from which all these patterns must follow. If there is a final lesson in the smallest things, it is that solidity, location, and even emptiness are not fundamental, they are outcomes. The universe does not present us with little stones of certainty, it offers statistical promises and then keeps them with astonishing fidelity. What we call a particle is a moment when a field leaves a record, and what we call a law is a symmetry that survives every test we can afford to perform. Somewhere beyond quarks, beyond the Standard Model's precision, beyond the Planck scale's glare, there may be a deeper order that makes today's inputs inevitable and makes space-time itself a derived phenomenon. Until then, the most honest picture is also the most mysterious one. Reality is not built from things, but from relationships, and the deepest layer may be not a substance, but a rule we are still learning to read. If you want to follow this story further, watch the anomalies, the precision measurements, and the sky itself, because the next revolution may arrive as a faint deviation, not a dramatic new particle. In the cold open, we asked, when we peel reality back past atoms, past electrons and photons, and reach quarks and fields, are we finding the final building blocks, or the edge of what can ever be known? The answer so far is both, because what we find is not a last object but a deeper description, where particle is a convenient word for a quantized ripple in a field, and the edge is real, not as a wall of ignorance but as a principle, that to ask smaller questions we must spend more energy, until space-time itself may answer by changing the rules. So what is everything made of beneath atoms and beneath subatomic particles? It is made of excitations in quantum fields, stitched together by interactions, and constrained by symmetries that feel like laws because they are the universe's most reliable habits. Yet those habits are not complete, because gravity still stands apart, dark matter still hides its identity, and the constants we measure still refuse to explain themselves. Our question becomes sharper now, not what is the tiniest thing, but what is the simplest set of rules from which all these patterns must follow. If there is a final lesson in the smallest things, it is that solidity, location, and even emptiness are not fundamental. They are outcomes. Until then, the most honest picture is also the most mysterious one. Reality is not built from things, but from relationships, and the deepest layer may be not a substance, but a rule we are still learning to read. If you want to follow this story further, watch the anomalies, the precision measurements, and the sky itself, because the next revolution may arrive as a faint deviation, not a dramatic new particle.